بندر الرجاء من الحضور التوجه إلى الجلوس. الرجاء من الحضور التوجه إلى الجلوس.
Please make your way to the main auditorium. We will start momentarily. Kindly make your way to the main auditorium. We will start very shortly.
Dear guests, please be seated. Dear guests, please be seated. Thank you.
الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. We would like to welcome the official delegations, participants, and the audience for the first international conference on the sand and dust storms that is being held in the capital of the Kingdom of Saudi Arabia, Riyadh. Now it gives me a great pleasure to invite His Excellency Dr. Ayman Ghulam, the CEO of the National Center for Meteorology and the supervisor of the Regional Center for Dust and Sand Storms, to give the welcoming speech in the opening of the conference.
بسم الله والصلاة والسلام على رسول الله سيدنا محمد وآله وصحبه من والاه. Good morning everybody and welcome you in our capital city, the beautiful capital city Riyadh. نبدأ على بركة الله افتتاح المؤتمر الدولي للعواصف الغبارية والرملية والإنذار المبكر منها، متمنيا وسائلا الله العلي القدير أن يجعل في هذا المؤتمر الخير والبركة لبلداننا جميعا، وأن تكون مخرجاته بإذن الله تعالى في صالح أوطاننا وللخدمة القضايا البيئية والاستدامة بإذن الله، على بركة الله.
Thank you, Dr. Ayman. Now it gives me a great pleasure to invite the first chairman of the first session this morning, Dr. Rami Al-Farra, to chair the first session titled Health and Environmental Impacts. Dr. Rami Al-Farra is a principal scientist at Qatar Environment and Energy Research Institute at Hamad bin Khalifa University. Dr. Al-Farra leads research on air quality, climate and human health. Now it gives me a great pleasure to invite His Excellency to the stage and and he will be inviting the panelists.
Good morning, everyone, and I would like to start by thanking the National Center for Meteorology and the Regional Center for Sand and Dust Storm for the kind invitation and for this landmark conference, which I hope it will be a start for regional collaboration to address this important challenge for our health, our economy, and our environment. And I'd like to start by asking and inviting the all speakers of the first session to join me here on the stage. Please come and join me. Dr. Tariq Hussain, Dr. Hiba Safi, Dr. Ali Al-Hamoud, Dr. Majid Al-Touhi, and Dr. Abdul Majid Haddad. Please. And it is my pleasure to start the conference with the first keynote, but can I ask please for the clicker? Can I have the clicker please for the slides? Yeah. Okay, so in this first talk, I'll hope to use the next half an hour. I'm sorry, I'm just waiting for the slides to move. So in this talk, I would like to look at sand and dust in the region from the urban air quality impact and the human health implication. And start with thanking all my collaborators from my colleagues at KIRI, Qatar Environment and Energy Research Institute, Qatar University, the Ministry of Public Health, and the H. Hamad Medical Corporation, my health collaborators. I hope by the end of this conference, I will be able to add a few more names for my next slide with more collaborations. I will also like most of you here will take this opportunity to connect and make new collaborations to help address this joint important topic that knows no borders and applies to all of us. In the session, I will hopefully give a brief outline about the importance of dust in the environment and talk about air quality, dust, and human health, specifically in urban regions. I will give an example of a research strategy to identify this important challenge in an urban scale, present some highlights, and then talk about a process for assessing the health impact before finishing with some key messages. Yeah, so in the first, when we talk about dust, of course, most of you here are very big experts in why dust is there, how dust is formed, and in dust regions, dust emissions have certain conditions, like our region unfortunately has many of them available quite a lot of the time for having strong wind, dry conditions, few like sparse vegetation, and saltating particles, moving particles, which whenever the wind picks up and these conditions exist, sun dust events at different scales are generated. In this talk, I will focus on how they impact the urban areas, the urban centers where people live, how it influences air quality, and of course the human health and the regional impact. So on the local scale, we live in cities and we get impacted by dust events, dust days. We breathe in dust particles mixed with urbanization emissions. How does this affect our health? How does it interact with the regional background of dust, with the urbanization, industrialization emissions, and what does this mean to human health? On the regional scale, dust, of course, has an important impact on biogeochemical cycles. It transports and deposits nutrients, nitrogen, phosphorus, that has impact on the ecosystem, on water, on soil and land. And also globally, dust particles in the atmosphere have a major impact on climate. Individual dust particles could either scatter back incoming radiation, contributing to cooling, counter-affecting some of the climate warming effects, or it can modify the microphysics of cloud and ice nuclei, affecting the albedo of the climate. And also, so in general, the current assessment that the net effect of dust globally is cooling, which offsets some of the climate impact. So on a climate scale, or a global scale, it has a cooling effect. On an individual local scale, it has implication on dust and on the environment, on human health and the environment. So the picture is quite complicated. At different scales, it has different impacts. And we need to understand them and for our region and for our individual cases. So I will just go quickly through some of what we know about the impact of human health on air quality and dust, and how dust impacts air quality as well. So it's known that we breathe in different types of pollutants, gaseous pollutants and particulate matter. Some of them are natural, some of them are man-made. And depending on the pollutant type, they can go through the respiratory system in different upper respiratory, the middle, and the deeper into the lungs. Certain pollutants, they penetrate very deep. They can go to the bloodstream and can affect all sorts of cardiovascular and the brain and other conditions. Dust particles, because they're mechanically generated, tend to affect upper respiratory system, but contribution of finer dust on the PM2.5 can go into deeper parts of the lung and have bigger impacts on human health. And we will talk about this a little bit more throughout the talk. The Global Burden of Disease study, this is a major study that quantifies the key drivers for the global burden of disease globally. What are the key factors, environmental and individual factors, that contribute to the total mortality and morbidity of the humans? And it showed In 2019, this global assessment that particulate matter, PM2.5, which is a fine component of dust, is the largest single environmental risk factor to health. It contributes to 7 million deaths annually. Looking at it, it's the second one up there. The first one is body mass index. On this list, you will see body mass index, diabetes, cholesterol, blood pressure, all the usual suspects. And air quality and particulate matter is up there. This is the 7th overall, the largest second environmental one, and our exposure to it is increasing. This is why in the pink color up there, the blue colors are factors that are decreasing in exposure, like smoking. But air quality is now, and dust exposure is one that we need to pay a lot of attention to in terms of health. And you see here, this is a study looking at how the concentration of particulate matter on the x-axis contribute to cause-specific mortality from different diseases. You can see stroke and ischemic heart disease, respiratory, and lung cancer. They have different parameterization, different relationships. And the important point here is any reduction we can achieve on the x-axis back to the left has a measurable health outcome by reducing mortality and reducing hospitalization. So there is a health outcome associated with any mitigation we can achieve for particulate matter mass. This particulate matter mass can be from dust and from anthropogenic sources. And this is what will be the source of the discussion I will provide later in this talk. And when we look at dust, there's a lot of perception that dust is natural, so we can't do anything about it and we shouldn't worry about it, it's just natural. But of course, the fact it's natural doesn't mean it's not harmful or it cannot be harmful. And this review article was prepared before the WHO recent guideline review. In 2019, they looked at all the literature related to dust and the impacts of dust on human health from a big major review analysis. And they found that dust has impact on cardiovascular and respiratory systems. Even clean dust in clean regions has been associated with allergies and impacts on human health. Very importantly, it found that dust can act as a vehicle for transporting biological material over long distances, bacteria, viruses, different types of biological materials. Dust can provide a surface for transportation over long distances. And crucially for our region here, dust as a surface can provide a medium for emissions from urbanization, industry, construction, traffic, man-made activities to interact on the surface of the dust, and that has been shown to increase the toxicity of dust. So dust itself is less toxic than black carbon, for example, but when it's interacting and mixing with urbanization emissions, the toxicity of dust increases. In this region, we live in areas, urban areas, where we have both strong dust events and strong urbanization. So that mixing is amplified. And it's our role and our duty as researchers and as community to understand this. Very few places in the world experience these conditions. In Europe, they have dust coming from Sahara, transported hundreds of kilometers or thousands of kilometers, being diluted and processed. We are at source regions, close to source regions of both urbanization and dust. And understanding this is very important. Quantifying this is very important. The WHO, when they finally recently reviewed their guidelines, they reduced the annual guidelines for particulate matter levels to 5 microgram for PM2.5, which is extremely challenging. 90% of the world population live in areas that has air quality higher than this. So this standard is it's not standard, it's a guideline. It's not legally enforced, it's a guideline based on health studies. Standards are often more higher because they're legally enforced. But crucially, they introduced interim targets. The interim targets from 4 to 3 to 2 to 1 can be as high as 35 annually. And we encourage people to think about interim targets and adopt interim targets as a way of progressively moving towards the guideline. So this guideline is not legally enforced, but it's important because it's based on health outcomes. In the same review, they looked at good practice statements. They said there are components in the particulate matter mass, because it's a mixture of different types of chemicals, that we don't currently have enough evidence to set guidelines for, but we know they are important for health. And this include ultrafines from aviation emissions, black carbon from combustion, and sand and desert storms. And in this, They put a very good guideline about improving the understanding of how we measure and monitor and report dust contribution to air quality, conduct epidemiological studies to understand its effect on health, and look at urbanization emission initiatives like greening, early warning systems to try and combat dust and desert storms. And this was really part of the research strategy that we've developed over the last 3 years in Kiri. And I would like to share with you some of this strategy, so hopefully it can be of use regionally as well. The main point of this is we look at across the urban area of Doha, which you see on the map here. It's about a 20 mile by 20 mile area. 2.5 million people, 2.7 million people live in this area. You can see we have a research network of 6 stations. A station upwind on the northwest in Shahaniya, and then stations across the urban area from regional urban centers to roadside to suburban and to urban background, and then downwind and another city called Al-Wakra. The reason we align these stations in this way is consistent with the prevailing wind direction. You see in the wind roses, the majority of the time the wind is northwesterly. This way we can understand what happens on the regional background, what comes to us transboundary from upwind countries, and then what happens across the urban area. We look at all sorts of air quality and dust measurements to understand this kind of picture. The idea is to understand the regional background, the national background on top, the urban background, and then the street level. We look at all the increments so we can quantify which pollutants come from where, and which of pollutants are natural, which are man-made, which are primary or secondary, and then hopefully develop strategies to mitigate and improve this. Crucially, we had to come up and establish a super site. Our Thumama Stadium super site, and super site is very important because it's not a regulatory site, it's not a standard monitoring. We add research grade equipment to help us understand the chemistry, the composition, the sources, the interactions that govern and control the formation of pollution, the interaction of pollutants, and understand the drivers, the processes, and how we can mitigate them from the chemistry and from the individual precursors. And we had to equip this super site with state-of-the-art equipment that allow us to look at the chemical composition in real time and also offline. So we used high volume and low volume samplers to give us the composition that most of you are familiar with. But crucially, we use real-time online state-of-the-art equipment that provide us chemical composition on an hourly basis or even 15 minutes basis. This allows us to understand the dynamics of the formation of the sources of the processes, daytime, nighttime, rush hour, afternoon, chemistry in the afternoon versus nighttime chemistry. So we get the detailed composition. We also have recently obtained an XRF-based instrument that looks at the elemental composition of all the components, the metals, and this is like you do with ICP MASPIC as a gold standard. This gives us in real time, every hour, we get the PM 2.5. With a 2 inlet, we switch between them. So we get the PM 2.5 and the PM 10. And I'll show you some of this later. We also look at black carbon for marker for combustion and bioaerosols, because dust and bioaerosols are very important. So the strategy simply was to look with a certain instrument, we get the PM1, the PM 2.5, and the PM10 measured simultaneously. And this is very important. We get all the 3 mass fractions measured every minute. So we have that information for all the PM fractions. We look at the the composition, the chemical composition, the black carbon markers. So we can build between these instruments in real time a very good approximation of how much is natural, how much is man-made in real time. And then we do more detailed offline analysis to verify some of the assumptions. The main assumption is the small particles in PM1 are mostly anthropogenic emissions, secondary and primary. The PM10 high fraction, so the supermicron are mostly natural, mechanical generation, sea salt, dust, and maybe some mechanical tire wear and brake wear. And the PM 2.5 has a mixture of both. So here's some of our results. Here you're looking at 3 locations, our urban background, our regional background, and our urban locations, measured simultaneously at the same time. The yellow is the PM10. This is our broxifier dust. And you can see the very large spikes that happen at the same time across the whole area, from the background, the middle of Qatar, to the middle of the city, to downwind of the city at the same time. This is a signature of regional dust event. And you can measure this simultaneously. We can quantify when dust is hitting the urban area. We can see how much does it contribute and how long does it last. And we can see small different types of event of dust. This scales, very big ones, medium ones, and smaller ones. When we convert this plot to the same data, but we look at the fraction of the PM1, which is mostly anthropogenic, and the PM2.5, which is a mixture, to the total PM10, you see here, the yellow is mostly the fraction of dust in the PM at the three locations, in the urban regional background, urban and urban background. The gray is the anthropogenic emissions from secondary and primary. And we can see here two things. Maybe we can simplify this and make it, this is hourly data, so we can get this very high resolution. I can make it daily, so the next slide. This is now the daily data of this. It's simpler to look at, and you can see the contribution of dust approximately to the total mass across the areas from regional to urban to background. And you see two things. The yellow tells you how much, 70% of the mass at times is natural dust. The purple to gray is an important relationship. When the gray is dominant, when the gray is more than, almost all of the purple is gray, this means we have domination of anthropogenic emissions. While when we have a lot of yellow, you see that the purple and the gray are separated because that's basically the dust is dominating. So this information allows us to understand with 1 minute data resolution to a very good approximation what is dust events, how much it is and how often. So we can convert this into a methodology to quantify dust events and dust days. This is very important when we do health studies. We need to know days that are impacted by dust, so we can understand the impact on the health, the lag effect, the next day, the day after, and after, how does it affect people? And that's what we do. In the next slide, we look at, on the PM10 on the x-axis, this slide should, this should all be an animation, but it's okay. I mean, it should be an animation, but it's okay. So move back, yeah. So on the x-axis, we have the PM10 mass. The y-axis, I'm looking at the fraction of PM2.5 to PM10. This y-axis is an indication of anthropogenic contribution. The higher the y-axis, the higher this ratio, the more anthropogenic influence. The lower it is, the more dust influence. And we can break this data into three areas. The area on the right-hand side, or the x-axis above 300 micrograms on the hourly data. And this is all big dust events. So we can quantify dust events based on just PM10 mass, hourly on the left and daily on the right. And then on the y-axis, we can go on the very top, at more than 70% fraction. It's all anthropogenic domination at low PM10 mass. And then there's a big part of the data where we have a background PM10 levels and a mixture of anthropogenic and biogenic over the period. Most of the time, dust events, big dust events, over 2 years of data is only 6% of the time. Anthropogenic domination, when we have very high anthropogenic, also 6% of the time. 88% of the time, we breathe in mixture, very balanced mixture of anthropogenic emissions and dust. And this is very important. The color scale there, you can see even the green, above 40% is more dust, anthropogenic domination. The one lower is mostly dust. So this data alone, without chemistry, without anything else, just having the PM1, PM2.5, PM10, allows us to quantify dust events, dust days, to a very good approximation. And this helps us in understanding, quantifying economic impacts, quantifying health impacts, understanding the impact of dust on anything. This is a metric we can develop, and we would like to validate this with visibility data, because visibility is the standard for defining dust. So this data can be validated against visibility and hopefully applied to different regions, different sources and locations in the region to see what are the thresholds for daily and for hourly, for PM2.5 applied to PM10. And that can be a methodology that can be adopted across the region to quantify dust days and dust events and how they impact human health, how they impact the economy and other things. And when we look at the composition to understand how much dust and anthropogenic affect the mass, at the suburban site north of Doha with very little urbanization, quite a small new area, for about a year of data, 70% of the PM2.5 was natural dust, while downwind of Doha, where all the emissions have, we see almost 50-50 split between anthropogenic and natural. So in the urban centers, dust contributes about 50% of the mass on average, and anthropogenic emissions and urbanization affect the other 50. But when you look at the hourly data on the plot, it can be very different. Sometimes dust is 70, 80%, anthropogenic can be 80%. So it's very dynamic, very changed, day to day changes a lot. On average, the picture is like this. And when we break this to chemistry, to components, we see that the yellow, this is monthly data for about a year and a half, we have collected so far. The yellow is dust, and you can see we have big dust events in spring. In April, May, we have more dust events. And then the anthropogenic is mostly sulfate in red. So sulfate is very important driver. Nitrate and sulfate and ammonium. These three components, secondary inorganics, are key drivers for PM2.5 mass. And for this, ammonia is a very key component for driving them from gas phase to particulate. So our understanding of natural dust and non-natural stuff, we need to understand the drivers from the emissions and the ammonia role in naturalization of acids into particulate matter mass. And this is our most recent equipment. When we measure now all the elements in real time, hour by hour, switch between PM10 and PM2.5, we can see calcium, aluminum, iron, sulfur, copper, all the elements. We do it in real time every hour. We switch between the two elements. We can calculate the ratio for each element between PM2.5 and PM10. And you can see sulfur, for example, the ratio is almost 1, which means all the sulfur is anthropogenic. On the other side there, we see calcium, we see iron, we see aluminum, very low ratio, which means it's all natural. So mechanically generated and natural sites will be on that side. Man-made combustion will be on the left-hand side. We look at wind roses, we look at the wind direction, wind speed to understand, in the bottom here, examples. Copper, for example, it's all around the center of the station, which means it's all from brake wear and tire wear. It's man-made pollution from brake wear and tire wear. On the left-hand side, in the middle, you see article like calcium and aluminum and iron. They are associated with very high wind speed and northwesterly. That's all dust emissions. So we can actually see what is these elements natural, what's man-made. We will take all of this data into a big source apportionment method to look at the sources and quantify the sources. That's our next step. Finally, I'll just quickly look at how we assess the health impact and what are we doing about this. And this is an invitation for everyone in the room from the region to hopefully play part in this. This is very important for the region. So if we click one more time on this, please. No, click on the video, please. Sorry, the next slide, and then play the video, please. Okay, this should have been a video, but I think they converted this to PDF. That's why it's not working anymore. If you go back one slide, and apologies for this. So this is a global simulation of PM2.5 dominant sources globally. The yellow and orange is dust, and you can see we live in a dust belt. Our region is impacted by dust mostly, and then you have green is organics, blue is marine sea salt, white is sulfur from urban human industry, and what we see when this is simulated normally, there's a lot of interaction. Each region has a specific dominant source, but there are interactions between the sources. And for us, all the health studies, all the evidence for the WHO guidelines are based on studies that are published from from America, from Europe, where mostly the composition is anthropogenic and biogenic. There's very little influence of dust on this data, defining the health guidelines, defining the impact on health. There are very little studies from our region representing our exposure to dust and interaction of dust and urbanization on health, and how that affects the standards, how that affects the guidelines. And our region is currently not represented in these guidelines. So the guidelines, very difficult to achieve for anyone in the world. For us, is more difficult because our high background of dust. But we need to understand if these guidelines really apply to us, and we need to understand the impact of dust on our health and how that should be translated to health effects and burden. What we need to do. So I have a research question. So are the health impacts of air pollution determined by the PM bulk mass, the PM10 or PM2.5 mass, or by the differential toxicity of the chemical components? If you breathe in 10 micrograms of black carbon or 10 micrograms of dust, is it the same? Are they mixing? So that's this question. And in this way, the WHO guidelines that are globally applied to regions that have very different compositions should be with enough data, with enough evidence and studies globally from different regions, should be accounting for differential toxicity of compositions, of mixtures, should be accounting for different components and weighted by the function of the different components. That's the question, and that's the hypothesis, the research hypothesis. I think bulk mass is a sufficient metric for determining health, PM10, PM2.5 mass, but this mass is determined by the composition of the mixture, and these mixtures are different regionally in the global scale. We need to do this regionally to understand how it looks, and then see what that means in terms of health impacts and translate that to guidelines.
2 minutes.
Okay, the last slide. Sorry. So what we should do, in order to do this, we need collectively to have 2 very high quality data sets: environmental data sets, air quality, climate, different environmental stressors, and health records. We need all natural death data, we need cause-specific death data, we need hospitalization data. All of this is happening. Most health organizations collect data on daily admissions and daily mortality and morbidity. They use them for their purposes. We have air quality data. Hopefully more and more people will have high quality data that we can trust, data that is validated and of high quality. So these things already happen in parallel. We need to join them. We need to do more across discipline collaboration. We're doing this in Qatar right now. We're starting to collect the data from the both communities, and we're trying to understand this. The WHO ran a workshop last week in Amman to introduce epidemiology analysis and train people on how to conduct this work if you have the right data. We need this to be done as many cities as possible in the region, so understand the impact of dust, urbanization, and the interaction on human health. But crucially, this gives us association at very high level. We need then to complement this with additional studies on cohort studies, exposure studies, toxicology studies, because maybe the signal in epidemiology might not be big enough to distinguish. We need more detailed studies where we look at areas impacted by urbanization and dust and differentiate between on the individual level. So we need to define and design more targeted health studies to understand this and hopefully feed this into policies and into regulations. And just the outlook, we live in a changing climate. Our region is expected to experience more heat waves, more dust storms. So all of this is becoming more and more relevant to us. And most of you are aware of the new ATTACH, the WHO launched in COP28 in Dubai last year, ATTACH, the new alliance for impact to climate and health. Climate change is no longer only about melting ice caps and rising sea level and polar bears. It's about my health, your children's health. The impact of heat waves, the impact of dust storms, and the amplification of these on our health is something happening to us now and will increase in the coming future, and is increasing as we experience changing climate. And here are my key messages. I'd like to thank you all for your attention, and we'll be taking questions, I think, later on. Thank you.
Thank you.
More of me again, so thank you very much, and we will go now to the next speaker. We will have discussion time at the end of the session for everyone. I would like to introduce Dr. Tariq Hussein, my friend and colleague. We've known each other for a long time, and he's now at the University of Helsinki. Please, Dr. Tariq.
Shukran jazilan. Assalamu alaikum. Good morning, everybody. So, today I'm going to extend the presentation of my colleague Rami and look at the size distributions and how to convert this information into inhaled deposited dose into our respiratory system. To go to the exposure, please, next slide. So the exposure and how to express this into something inhaled dose. We need to understand the pollution type, the medium of the exposure, and the pathogens that are going to enter our body, and finally the human components. And these are summarized in this slide. The next slide, please. So we try to combine these ones into a simple mathematical model as it's shown here. The four components are the pollutant concentration, which is the exposure level, the deposited fraction in the respiratory tract, and the breathing rate, or what is called the ventilation or the minute ventilation in the respiratory tract, and finally the exposure time. If we combine this into the deposited dose, so this double integral, which can be simplified into four components multiplied by each other's later. Next slide, please. And the respiratory tract, from atmospheric point of view, is divided into three regions: the head airways, the main airways, and what we call the alveoli, which is the deepest part in the respiratory tracts, where the exchange of oxygen and carbon dioxide is happening, and also other components while we are breathing. Next slide, please. And this shows how these particles that we are breathing, or particulate matter that we are breathing, enters our body and deposited in different regions. You could see, according to the region, the deposition pattern is actually different. And we can see that smaller particles can reach the alveoli more efficiently than larger particles, which are mainly collected in the head airways. Next slide, please. This table shows the minute ventilation, how much air do we breathe per minute or per hour. And this value depends on our health condition and also our resting or exercising. So the more efforts we do, we need to breathe more air, and this minute ventilation value is larger. If we think about adults compared to children, then the amount of the air breathed is also larger. So this allows us to understand how much of this air pollution is entering the body via the inhalation and exhalation process. Next slide, please. Here I show two extremes of observation that we see every day. The upper photo is showing anthropogenic pollution compared to clean conditions in a city, and the lower one shows dusty day compared to a clean day in another city. In both cases, visibility is kind of hindered, but also this kind of events affect our health in different ways. Next slide, please. And here I will present, according to our observation, how the size distribution would look like during dust episodes. Next slide, please. According to our observations in Jordan, in the capital city Amman, this dust episode was characterized to come from Saharan area in North Africa. And the upper plot shows the time on the x-axis, and on the y-axis the particle size. The color red is more concentration and blue is less concentrations. And you could see during the time with high concentrations, red, you can see in the lower figure how the particle number concentration is varying and reaching values exceeding 10 particles per cubic centimeter. If we think about the background, how much would it be in the air? Usually it should be less than 1 particles per cubic centimeter for the large particles that are within this measurement range that I'm considering between 1 micron and 10 microns. Next slide, please. The Saharan dust gets more intense on the next days, and you can see the back trajectories which are shown in the middle, how the source area is now getting more evidence that the air mass is bringing the dust from the Saharan area, and the concentration is building up in the atmosphere. And the values of these dust would increase even more if we go to the next example. So next slide, please. More. The next example is about dust episode, which is more local compared to that one, from the Levant area, which is called Bilad al-Sham in Arabic. Next slide, please. So this dust episode is actually originating from nearby sources of dust, which are located in Syria and Iraq and North Saudi Arabia. And you can see the sharp peak just appearing and disappearing quickly, not like the Saharan dust, which stays for a longer time but lower concentration. Here we have higher concentration exceeding even more than 20 particles per cubic centimeter. Next slide, please. And if we think about Saharan dust combined with Levant source regions. Next slide, please. You can see this example, how much the red color is getting, and in this case, the concentration crossed the border of 100 particles per cubic centimeter. And you can see from the back trajectories, the beginning of this dust episode is coming from Saharan area and sometimes making circles in the Levant area. Next slide, please. And even goes deeper into the Levant, reaching areas from South Iraq, Kuwait, and Ahvaz. Next slide, please. So the overall picture, how to combine this exposure level of the coarse particles or the micron particles into health and health assessment data. And if we summarize the particle size distribution of these dust episodes, we can say that dust particles can be characterized by two modes. One of them is in the micron size. Its geometric diameter can be 2.5, 3 microns, and the number concentration varies between 10 and 100 particles per cubic centimeters. The other, no, the previous one, please. The other mode is the accumulation mode, which is smaller than 1 micrometer in geometric mean diameter, but its concentration is even more, ranging between 100 and 1,000 particles per cubic centimeter. Next slide, please. If we combine the values of the exposure with the exposure time, then we can think about a parameter called the dose rate, which is how much of material is entering the body per hour. And according to that, the total dose, and here total dose I mean for all particle sizes and also all respiratory region, regardless of it is red airways or main airways or alveoli. So the value varies between 2 to 15 milligrams per hour during rest, if somebody is sitting or standing. But if we are making more exercises, then the value gets more, increasing from 30 up to 155 milligrams per hour. So one day exposure during a dust episode can get information from this by multiplying these numbers by 24 hours. And if we think about where is this deposited more, we discovered that during rest, more of this, or most of this, about 46% of these values are actually reaching deep into the lung, the alveoli. But during exercise, most of it is deposited in the head airways, about 66%. So, to this point, what is next? Now we know the values. The next is to characterize the chemical composition of the dust particles and then see how it's going to affect our body, our human health, and what can be done to reduce these values in the future. Thank you very much.
Thank you very much, Thank you, Dr. Tariq. I'm pleased to invite to the stage now Dr. Hiba Safi from the WHO Regional Center for Environmental and Health Activities in Amman, Jordan. Dr. Hiba, you have 15 minutes. Thank you.
Okay, many thanks, Dr. Dami. Thanks for the organizers for the invitation to participate and contribute to this conference. Good morning, dear esteemed experts and colleagues. In my talk, I'll touch briefly about the health impacts of air pollution in dusty environments, our region. Next, please. Okay, just for who are not familiar with the WHO Eastern Mediterranean region, we are consisted of 22 countries distributed among 3 parts: African region, Middle East, and Iran, Afghanistan, and Pakistan. So we have a very diverse, let me say, region with different socio-economic and demographic variation. Unfortunately, around 50% of our countries are witnessing one or more than a type of emergencies, whether political or natural emergencies. Next, please. Okay. Every year around environmental health burden counts for around 25% of the total burden of disease at the global level as well as at the regional level. Every year we lose around 1 million premature deaths due to exposure to several environmental health risks. And as you can see, air pollution contributes to more than 56% of these premature deaths. Unfortunately, climate change is now exacerbating these health impacts, so we are expecting an increase in these figures. Next, please. Okay, WHO updated its air quality database in 2022. It estimated the population-weighted exposure for PM10, PM2.5, as well as NO2, based on a structured methodology. The upper part of the graph represents the annual concentration, population-weighted concentration for the air pollutants. As you can see, the Eastern Mediterranean region has the highest PM10 concentrations as well as NO2 concentration levels among the other WHO regions. The lower part of the graph represents the number of settlements which is the national monitoring stations reporting to WHO. As you can notice that the Eastern Mediterranean region is the second lowest region among the other region, which is, let me say, we need to enhance the monitoring networks at the regional and national levels, as well as to enhance the reporting of these figures. Next, please. This slide elaborates the anthropogenic with non-anthropogenic components of air pollution, or the population-weighted exposure of air pollution, which is the SDG 11.6.2 for WHO regions. As you can see, dust contributes between around 10 to 15 microgram per cubic meter from annual concentrations in our region, which is a high major source. Next, please. Okay, WHO as well as a custodial agency for reporting to the SDG 3.9.1, which is the age standardized mortality rate due to combined air pollution, which is ambient as well as indoor air pollution. WHO estimated the mortality rate for the total 5 main diseases that interlinked with air pollution, namely stroke, lung cancer, ischemic heart disease, chronic obstructive pulmonary diseases, as well as the acute lower respiratory infection. If we looked at the Eastern Mediterranean region, it has the second highest mortality rate, age standardized mortality rate for the total mortality. And ischemic heart disease contributes to around 50% of the rate. Next, please. Okay, as we all agree that sand and dust storm is a major source of air pollution in the eastern Mediterranean region. Unfortunately, so far there is no precise distinction between sand storms as well as and dust storms, since there is a continuum of particle size in any storms. However, WHO and the joint WHO and WMO reports shows that dust contributes to around 30 to 50% of the total concentrations of PM10 and PM2.5. Next, please. As my colleague Dr. Rami mentioned previously, WHO, or we at WHO, updated our air quality guidelines in 2021, and we lowered, or the experts lowered, the air quality guideline values for the key air pollutants, PM10, PM2.5, NO2, SO2, and ground level ozone. And that's because that the recent evidence and the epidemiological studies shows that air pollution causes adverse health impacts at very low concentrations. So this is the evidence that carried out over the past 15 years. Unfortunately, we didn't manage to have some, let me say, quantitative guidelines, particularly for sand and dust storms, because there is insufficient evidence, whether quantitative or qualitative, to identify the health burden of sand and dust storms. That's why WHO provided a section for good practices for the emerging issues or concerns, including sand and dust storm. Next, please. The good practices of sand and dust storm as recommended by the air quality guideline, it is listed in 5 main points, which is maintain air quality management and dust forecasting management or programs, maintain air quality monitoring programs and reporting mechanisms. The most important, I think, point from our side, okay, thank you. It is to encourage conducting the epidemiological and toxicological research to better understand the health impact of sand and dust storms or air pollution in dusty environments. Implement wind erosion control through careful expansion of green spaces. The 5th and the last recommendation, we are not fully supported, but that was agreed by the experts, that to clean streets and urban areas with high population density and where rainfall present, sorry, I can't see the screen, resuspension by road traffic. This recommendation is a challenge for our region in terms of the lack of water resources, intensity and the frequency of dust storms, so we don't feel that this is applicable for our parts of the region. Okay, the United Nations Coalition on Combating Sand and Dust Storms, I don't want to talk thoroughly on this because my colleagues from FAO, Dr. Firas Ziadat, and WMO, Dr. Sarah Sarat were already talk about this. But it's worth note that based on several UN resolution, the 19 UN institution developed the United Nations Coalition on Combating Sand and Dust Storms. It has 5 main working groups on several aspects, including health and safety, which is led by WHO. However, the whole coalition now is led by our colleagues in FAO. Okay, as a part of this work, the UNCCD produced Sand and Dust Compendium, which contains several aspects related to the compacting sand and dust storms at all levels. WHO wrote or contributed in writing a full chapter about the health impacts of sand and dust storms, which to summarize the recent evidence on this. Okay. Just in a very few, the recent evidence, unfortunately, so far, there is no studies elaborates the long-term or the health impacts related to the long-term exposure of sand and dust storms. However, we have a few researches about the short-term health impacts. Regarding WHO commission to conduct a toxicological review for around 52 experimental studies, experimental toxicological studies that shows the linkages between exposure to sand and dust storms and the health impacts. The evidence shows that there is a correlation between exposure to sand and dust storms, short-term exposure to sand and dust storms, and exacerbation of asthma, hospitalization of respiratory infection, as well as seasonal allergic rhinitis. Regarding epidemiological reviews, again, we don't have an epidemiological reviews that shows the long-term health impacts related to exposure to sand and dust storms, but the current studies or the current epidemiological reviews shows linkages between exposure to sand and dust storms and cardiovascular mortality, as well as respiratory morbidity. So this is, I think, a call for our researchers in the room to enhance or to conduct researches, epidemiological studies to better understand the health correlation between exposure to air pollution in our dusty environments and the health outcome. A part of our work in WHO, we have a technical advisory group on specifically on desert sand and desert storm. Led by our colleague from Lebanon, Dr. Najat Saliba. She's the chairperson of the technical advisory group. Under this group, we conducted 2 scoping reviews. The first one is to identify the pattern of sand and dust storms that should be taken in consideration in health studies. And the other one is to summarize the health impacts or the evidence about the health impacts of exposure to sand and dust storms. The main focus on the working group are listed in this slide. I won't, for the sake of time, take too much in considering this, but I hope your time will be allow you to read it. The research priority at regional level on desert dust and health is to have time series analysis of air pollution. That's to improve the understanding of health impacts of exposure to dust storms. Having studies to identify the impact of climate change on the sand and dust storms to better understand the impact of climate change on sand and dust storms, whether increasing frequency, intensity, the other relation, how can dust storms affect the climate change by cooling temperature, as already mentioned by our colleague. It is a real need, having a long-term effects studies, which is epidemiological studies, to estimate the long-term or the association between long-term exposure of air pollution in dusty environment and the adverse health outcome. From our side, last week, we conducted a regional workshop for around 7 countries of the region. The main regional workshop objectives were to building countries' capacities on epidemiological studies, particularly time series analysis for investigating or studying the health burden or the short-term health impact of exposure to sand and dust storms. The second one is to encourage countries to conduct a multi-country time series analysis to better understand the impact or the regional health impact of sand and dust storms. So far, 7 potential countries, namely Egypt, Iran, Jordan, Kuwait, Lebanon, Morocco, and Qatar, agreed to develop national time series analysis and to be at least distributed internally among their stakeholders. And our main objective actually to conduct a multi-country time series analysis. So far, 4 countries, Iran, Jordan, Lebanon, and Morocco, got their ministerial approval to be a part of a multi-country time series analysis for conducting a time series to link the mortality from all natural causes with the PM10 exposure for at least 5 years. So this is a call for other countries who are interested to whether have a national time series analysis or would like to be a part of this regional work. Just let us know and we will organize immediately a workshop or arrange for a future collaboration. That's what my talk, and thank you. Thanks to all.
Thank you very much, Dr. Hiba, for this excellent talk and for sticking to time. Our next speaker is Dr. Ali Al-Hamoud from Kuwait Institute for Scientific Research, Qasr. Your floor is yours and you have 15 minutes. Thank you.
Assalamu alaikum. I will present, inshallah, now my presentation. It is long, many slides, but I will go through many slides very fast. Because this is really a 7 years research بحث لمدة 7 سنوات في معهد الكويت للأبحاث العلمية. Here I will talk about the transboundary sand and dust storms, and I will present what research we have conducted for the past 7 years. I will go through these slides. First I will talk about the Arabian Peninsula, then I will talk about the sand and dust storm levels and the SDS affecting Kuwait, and then susceptibility maps, and then the health impacts. As we can see here, basically there are 10 sand and dust storm sources affecting the Arabian Peninsula. One, of course, from the Rub' al-Khali, this is the largest one, the empty quarter. Then we have from Syria, then we have from Mesopotamia, Iraq, and then there is also from western coast of Iran, Jazmorian in Iran. There is also from Pakistan-Iran border. Also there is from Rajasthan, India, and also two sources which come from Egypt and Tokar, which affect Jeddah. In other words, the Arabian Peninsula is affected by two local sources, which is the empty quarter and South Iraq, and 8 which are from outside. Now, the beauty about these images that I will show you, because these images have high resolution, high spatial resolution. For example, 250 meters in all satellites, remote sensing, or from aerosol optical depth aerosol, it is by 10 kilometer by 10 kilometer. But this 250 meters, which is very high spatial resolution, and you can see the dust storms coming from South Iraq toward Kuwait, toward Saudi Arabia, and also there are dust storms also from Qatar affecting down. This is also another source, as you can see, from Al-Ramadi in Iraq, and going to Iran, and going counterclockwise toward the empty quarter, and this huge dust storm only stopped by Al-Najran mountains, Jibal al-Najran, and you can see this huge dust storm. Also, this is a source from Iraq-Syria border, and you can see the one on the right side, you see this very smoky, looks like a smoke, but it is, in other words, wind-eroded dust events. This is in 2012. Another source which come from Rub' al-Khali, and this goes counterclockwise, affecting Oman onto the Arabian Sea as well. Another image also come from Rub' al-Khali, and you can see this is counterclockwise, affecting also Oman and the Arab Sea, and goes to Iran. This is another interesting image. This comes from actually Iran, from the Sahel of Iran, West Iran, and affects Oman and affects also Emirates. And you can see the one on the right side, this is very high spatial resolution, 250 meter, and it covers the whole, it covers the Arabian Sea, Khalij Oman. Another image also you can see that comes from the west, Iran, affecting as well Qatar and Emirates. Another image, as you can see, both images, you can see the image is so huge that it covers an area of approximately 600,000 square kilometers of the sea. So not only the land, but also the sea. Another area, this one comes from India and Pakistan, heading toward Muscat and Ras Al Had في Oman. This image, as you can see, تغطي Nile River. So this from Egypt, going through Red Sea, البحر الأحمر, Red Sea, and goes to Jeddah. Another image also from Sudan, and goes to Jeddah. Why I show you these images? Because these images has very high spatial resolutions, 250 meter, using modest satellites images, Echo and Terra. Some slides I will go, and this also we published it in this journal very recently. This paper has been published. Now the second study is we looked into the surface dust concentrations in the region. And we notice here for Kuwait, when we compare Kuwait, Iraq, Saudi, Iran, and Syria, Kuwait has the highest surface dust concentrations in comparison between Iraq, Saudi, Iran, and Syria. The highest surface dust concentration is located in Kuwait. This image shows that Kuwait has the highest surface dust concentrations, followed by Saudi Arabia, and also the highest wind speed in comparison with the other 5 countries. Lowest NDVI, and so on. This is a time series from 2001 and up to 2017 or 2018. And also there are some periods of sand and dust storms. There is drought period and wet periods. This shows that the dust level, using satellites images, the dust level in Kuwait is affected by the dust level in Saudi Arabia, as well as the dust in Kuwait. In other words, Kuwait is affected mostly by South Iraq, as well as by the dust concentration in Saudi Arabia. We did a study related to the high split, and we can see that during different seasons, for example, when we compare January in the winter and June in the summer, we notice there are differences in terms of what are the concentrations. For example, from June on the right side, you can see that the dust levels come from Shamal winds through Iraq to Kuwait. But when we look for the cold season, like in January, it comes from 4 different sources. And also the concentration, the dust concentration also differs. For example, when we look at January, the pollution in Kuwait mostly from local. But when we compare it for June in the summer, the concentration is regional. Again, this gives the same information. And this was published also in the Science of Total Environment with University of Harvard. Now the third study, we want to look now, after we look at the 10 sources in the Arabian Peninsula, we want to look at one of the 10 sources, which is the South Iraq. So this image, as you can see, it has, we compare it, we say it's like a waterfall, but rather than waterfall, it is dust jet. This dust jet comes from South Iraq into Kuwait and goes up to 1,200 kilometers, reaching Qatar. This is local. Also, there are some local sources in Kuwait. As you can see, there are 2 sources in South Iraq. the one on the right is brownish because from agriculture, and the one on the left, it is kind of whitish because it's more of dusty. And this is in 2021. This is in 2011. Another image, 2012. Also, the brown one and the yellow one. We have been following this through remote satellite sensing. Satellites. This is in 2013 as well, from South Iraq. And we noticed that during the dust event, then it continues for 3 days. That's why it has on the red on top, this is a dust event. So it continues for 3 days. Interestingly, this picture in 2018, we don't see the brown. The brown color which was on the right side, it disappeared. Why? Because there is now إعادة الأهوار في العراق. So there is more water on the right side. Now only that left side, this is the more deteriorated hotspot area. As you can see in 2018, this is the hotspot area, but now we are looking at 250 meters. As you can see, this is from Sentinel, and you can see the severe dust jet, which is like powdery. This is in 2021. This is in 2020. This is 2021. As you can see, the one on the right side is disappear. There is only one dust jet which affects Kuwait now, mostly. So this is the area. The area is 1,600 square kilometer. So in April 2019, me and my colleague, Dr. Ali Doseri, we visited the area in Iraq. Then we collected soil samples. This is the area, and these are the sample locations. And we can see the one on the red color represents vegetation. Red color represents zara'a, vegetation. And the white hotspot, this is the severe eroded area. And in 2004 to 2019, in 15 years, we can see this image also from satellites, and we noticed that basically the hotspot in 15 years has been shrinking, which is good. It means there is some vegetations around the area. And this is photos of the area after rain. This is after rain, and you can see in the background, this is sand dune, Kuthban Ramliya. These are some excavations during rain. And this paper also we published in Science of Total Environment, and also another paper we published last month. Now what we are doing, now we will go more zoom to the area. So basically I'm taking you from the Arabian Peninsula 10 sources, then to one of the sources which is South Iraq. Now we will go into more details, not 250 meters, but 10 meters, 10 by 10 meters. And this is the area. As you can see, you see the line in the middle, which is yellow. This is the highway. And this is also from Landsat, zoom in. This is the area and the vegetation around it. This is the area as well, close to Al Samawa city. And the one on the right side, this is from Landsat. This is in 2023, only last year. Why these images are good? Because the resolution is very high. Unlike the aerosol or AOD, where the resolution is 10 kilometer by 10 kilometer, as big as Kuwait City, only one resolution. Here we are looking by 10 meter by 10 meter, so we can very specifically look into the area itself. There's another also Sentinel 2023, and this is the NDVI. And you notice now when we zoom into the area, we can see the hotspot area, the one in the north and in the south. These are the more deteriorated. And this is very important because the area is 1,600 square kilometer. But within the area, there are more severe hotspots which we should consider. and we should spend money on to rehabilitate. And this is the area when we visit. So we visit, me and Dr. Ali Doseri and Peter, in May 2023. This is our visit with the universities. We took some soil samples, and we visit some of the villages around, and this is the area itself here. And you can see there are some sparse vegetation after rain, but this is the degraded area, one of the 10 sources. But you can see as very quickly when the car or when we walk, the soil is very fragile, mostly clay. So any wind erosion, it emits dust. And we took samples again in 2023. Then we analyzed the samples. Basically, we did physical soil analysis. And the physical soil analysis shows that the samples that we took mostly are clay. Then we did also chemical soil analysis. And we noticed there are 2 sources in the area. One is the dust sources. We determine it from the elements, which is aluminum, silica, iron, and so on. And also there are anthropogenic sources on the right side. How do we know it is anthropogenic? Because when we analyzed it through XRD, we noticed that it has chromium, it has manganese, nickel, vanadium, copper, and lead. And these are sources of anthropogenic sources. We did physical, chemical, and radiological إشعاعي, and we found out that using XRD, that these are we call them the daughters of uranium and thorium. So the daughters of uranium and thorium are very similar to other dust areas in the world. Then we did dust source susceptibility using machine learning. So this area we did with the 5 minutes? Okay. We did dust source using machine learning. We did, for example, many different parameters like surface soil temperatures, moisture, precipitations, vegetations, soil texture, land use through machine learning from satellites, and NDVI and wind speed. And we did 4 periods. There is a dry period, 2000-2004, wet period, another dry period, and wet period. In other words, from 2000 to 2021, there is not only there are dry periods, but there are 2 dry periods and 2 wet periods. And we analyzed, and we came with this high susceptibility index, which says that precipitation, NDVI, and wind speed are the most susceptible. And this is our area through using machine learning, الذكاء الاصطناعي. ولكن الذكاء الاصطناعي, it was not very good as much as remote sensing. Why? Because it shows almost 3/4 of the area is the degraded area, but this is not correct. Remote sensing through visual remote sensing is more important than artificial intelligence. And this is why. We noticed from hotspots, there is one on the top and one in the lower. There is one in the green and the north up in the north center, and also in the southwest. These are the major hotspots. And we used normalized difference vegetation index, land surface temperature, aerosol index, and another aerosol index through 2023, and using NDVI. And then we used also soil types through remote sensing, and we analyzed terrain elevations, and we analyzed moisture index, and we came up with these sources. Now this study I will skip, because this one looks into the economic impact of soil and dust storms on oil sector. We did the study, and this is me in some of the images here standing, and this study shows basically some of the severe dust storms affecting Kuwait. And this is my colleague, Dr. Ali, and me. And also we published this paper. We determined that the cost on only the oil sector in 2 years is $9 million from sand encroachment, زحف الرمال على القطاع النفطي. and we published this paper also. The sixth study, we used Harvard samplers and to analyze the PM 2.5, and we notice this is using source speciations. We did two studies, one in 2008 and one in 2020 and one in 2023 to determine what are the sources of PM 2.5. And we notice, for example, in the US on the left side, the sources are mostly from traffic and sulfur. But in our area, the sources are mostly regional and dust. This is also elemental analysis from our PhD student, Kuwaiti, studying in University of South Carolina. And we came up that basically the dust has the highest, about 40% of PM 2.5 is from dust. And we published this paper also last year. We published another paper also last year. And we did a study during the lockdown, but I will pass this, خلال فترة الحظر. And we to determine the PM 2.5 and PM 10 خلال فترة الحظر during lockdown. And we came to the conclusion that basically the dust, even during the lockdown, the dust and the temperature and the wind are the most triggers for PM 2.5. And then we have done also another, and we published the study as well. But where do we get the data? We used remote sensing because I don't have much time, and we predicted PM 2.5 in Kuwait and Iraq because there are so scarcity of data. So PM 2.5 across all Kuwait and across all Iraq, now we have the data, not from ground monitoring stations, but from satellite remote sensing, and we published these papers as well. And lastly, we have done using the WHO air quality model to determine the toxicological effect of PM 2.5 and PM 10. And I will have only 1 minute to finish. And we published this paper as well. There is not much time, I know. We published another paper. And my last presentation basically will talk about the health impact of mortality and dust. We have a publication here, and we noticed that non-Kuwaiti male and during adults, they have higher risk of death. We did another study of PM 2.5 and mortality as well, cardiovascular diseases, and we came up with some conclusions. We did also another study of PM 2.5 and hospital admissions, and using these samplers. And also we came up with another study during the sources, and we determined that dust is the major contributor with the respiratory, and we published these papers as well. And this is my last presentations. And what I say here, this is the conclusion. We need to characterization of desert dust properties using remote satellite remote sensing, because as I showed you, more of the aerosols and most of the studies around the world, they are using very low resolution, 10 kilometer by 10 kilometer, but through remote sensing, we are using 12 satellites, and we can go down as 10 meter by 10 meters. And the second one is we need to cooperate to assess PM 2.5 and health outcomes. And the third conclusion, KISAR can cooperate with the GCC to tackle the other 9 hotspots, because now we are almost finished with Mesopotamia, Iraq. And there are also 9 other hotspots that we can cooperate with the GCC. Thank you very much.
Thank you very much, Dr. Ali, for this very comprehensive presentation. Next, I'm pleased to invite to the stage Dr. Majdi Al-Touhi from the Sand and Desert Storm Warning Regional Center and the National Center for Meteorology.
Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. I will try to be fast as much as I can. My talk today is about estimation of the basic reproduction number. We call it R0 or RO. And my question is coronavirus airborne or not? Now, I have only 4 subjects, which is what is What is airborne? Microorganism defined as airborne, reproduction number, and is coronavirus airborne. What's airborne? Airborne transmission, spread, passage of pathogen from a source to a person through an aerosol, spreading infection from a person to a person with or without the disease. But the aerosol is a suspension of solid, liquid, and gas particles with particles size from 0.001 to 100 micron, and include and spreading the infection with the aerosol, which contain sometimes pathogens. Now, if we look at this picture, we see large droplets, diameter starting from 60 millimeter, more than 60, less than 60 millimeters, and less than 10 micrometers. And it depends on the distance and the size of the aerosol spreading, either through cough or a sneeze or through a talking behavior. Now, the mechanism of aerosol transmission of any infection agents, it depends on the size and the time, the size and the time. Okay. As much as we go, the size, for example, if we take size between 1 and 3 micrometer, actually it's difficult to see it from here. Size between size between 0.02 to 100 micrometer. The infection agents from patients can be split as individual or clusters of naked organism to disseminated skin cells. Transmission from respiratory tract from one person to another, it depends on the airborne, and is there any sufficient amount of this microorganism to cause the disease? Now, if we take an example, 4 kinds of organism, we have the the tuberculosis. The nature of the tuberculosis is a hard organism with a thick wall. It stays longer period of time. If we take the measles or varicella virus, it has a lipid envelope and it has a short and sensitive temperature relative to the humidity concerning the humidity and the ultraviolet radiation. All these outside environment affect on the transmission of the microorganism. If you take the polio, which is very lethal microorganism, poliovirus, it has no lipid envelope and it survives longer. Influenza, for example, it stays about 24 or 48 hours. It has hard and porous surface like stainless steel and plastic. And these are the picture of the microorganism. It depends on the size and the distance. Okay. Also, there is another factor, which is the dose. The dose of the microorganism is very important. Brucellosis, we need only 10 to 100 between 10 and 100 organisms to cause the infection. Q fever, 1 to 10. Viral hemorrhagic fever like Ebola, we need only 1 to 10 microorganisms, and so on. We go to Mycobacterium tuberculosis, we need only one organism to cause the infection. One organism. The basic reproduction number, it's a measure epidemiological tool used to estimate the average number of new infection caused by a single infection individual in a susceptible population. This is the definition. And it represents the potential for a disease to spread within population. Mainly, it is the average number of secondary case, yani the case which affect another case which cause the disease by one infected individual introduced into a population. Now, the R note, the scientists use the RO to describe the intensity of the infection, of the infectious disease. In case of outbreak, like what happened during corona epidemics, and the RO estimates have been important in part of the characterizing the pandemic or large publicized outbreak, including what happened in 2003 in SARS and 2009 influenza pandemic and the 2014 in Ebola. And it is something the epidemiologists are racing to nail down about the COVID-19. If RO less than 1 and if RO more than 1. This is the trick point. If it's less than 1, it indicates that average each infected individual will infect fewer than one other person. If it's more than 1, it implies that each infected individual will infect on average more than 1. This is the point. And this example of RO3, which is the first infected person will infect 3 persons, then will infect 9 persons, and so on and so on. In 1950, the epidemiologist George MacDonald proposed this phenomena on the malaria. If its RO is less than 1, the disease will die out in a population. Why? Because on average, an infection person will transmit fewer than 1 person susceptible. And on the other hand, the R0 or the R0 is greater than 1, the disease will spread. Now, the RO, the phenomena of RO represent a potential of transmission. This is the key point. How the organism will be transmitted and how the organism will infect more population. And this is a simple compartmental mathematical disease. They call it SIR epidemic model. It's SIR model, and all this definition of the susceptibility, infections, recovered, and so on. They use this model to detect if this disease is less than 1 or more than 1. Now, viruses such as COVID-19 are likely to spread in the air within a formation of liquid droplets more than could freely transport within the viral contents. Now, if we debate about virus like corona, is it airborne or not? It depends on the society, and it depends on the country, and it depends on the mathematical equations. We have direct and indirect aerosol transmission. The presence of particulate matter can stimulate the expression of transmembrane serine protease. It's called TMRSS2. And also, the transmission is affected by what we call it ACA2, the angiotensin converting enzyme, which bind the sites on the facility of infection. Now, each virus has transmission behavior, and it has sites which attach to the skin and then interfere inside the skin. If we block the transmission between the skin and the virus, then we control the virus transmission. SDS, sand and dust storm, can increase the level of PM 2.5 as well as being a vector for fungal disease. They are vehicle, as Dr. Rami said. The sand and dust storm are vehicle. It's a car, sayyara. They can transmit the disease, but it depends on the size of the organism and the size of the virus. Direct and indirect aerosol transmission, they speculate that the particles responsible for carrying COVID-19 were transported from considerable virus source greater than from Wuhan, China, towards nearby countries. They think that if the source in Wuhan, and this virus transported through sand, dust, riyah, any kind of vehicle through the world, but the study suggested that the primary deposition of the dust particles, carrying the virus depends on the interaction between the jet stream and regional meteorological system leading to COVID-19 outbreak in the different countries along this latitude belt. But myself, I've been working and dealing with COVID-19 many times. I don't believe that airborne COVID-19 is airborne. This is what happened in Sri Lanka and India, Cameroon, Nigeria, Saudi Arabia, and these are the papers and the research being done. In Sri Lanka, the RO was less than 1, between 9 and 1. In India, it's less than 1. In Cameroon, 1.07. In Nigeria, 4.84. In Saudi Arabia, 1.29. And also between 1 and 1.45. Shukran.
Thank you very much, Dr. Majdi, for your talk. And finally, I'd like to welcome to the stage our final speaker for this session, Dr. Abdul Majid Haddad, the Deputy Regional Director for the United Nations Environmental Program, UNEP.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, and thank you very much for the invitation. Thank you, National Center for Meteorology, His Excellency Dr. Ayman Ghulam. Thank you very much for bringing me to the issue of sand and dust storm after a long absence. For those whom they know me, we started in 2012 a regional program to combat sand and dust storm. My starting point actually is that sand is different than dust. So dust is really the focus, because dust travel long distances and it stays in the atmosphere for a long time, and it has the most health impact, as we can see from the papers presented here. So back in 2012, I was determined to actually make a difference in the region. And I mean the region is West Asia. To the extent that I put in my Skype slogan, I hate dust, I'm working to solve it, and please join me. In 2012, we started a regional program in collaboration with WMO, the United Nations Environment Program, and the WMO, and we published a report that was actually the baseline for the status of sand and dust storm in the region. In 2013, for the first time, countries in the region, and our definition of West Asia region is a little bit broader because of the dust phenomena. So the West Asia region was the GCC countries, plus Al-Mashriq, plus Iraq, plus Iran, plus Turkey. So in 2013, all these regions came together, and I think we have some audience here. They participated in the technical meeting that has happened in Abu Dhabi, in which a regional program was presented, debated, and so on and so forth, and there were good recommendations actually to collaborate among countries. And in that meeting, a baseline actually emerged, a baseline of sand and dust storm in the countries emerged, and specifically, countries came with a status report that shows the source of dust in these countries. Then in 2015, 2014, UNEP supported the development of the regional program, and actually we had two initiatives at that time. One is to support Iraq to develop a national program to combat sand and dust storm, and also we commissioned a study in the Islamic Republic of Iran to identify hotspots, sand and dust storm hotspots in Iran. In 2015, UNEP submitted a proposal to the Global Environment Facility for funding. It was around 5.6. It's a seed funding to start a regional collaboration, but unfortunately the funding did not come through. So at that time, I collapsed. But fortunately, since that time, I have seen considerable progress. First, on the global level, it is now recognized as a global phenomenon, a global problem, like desertification, like climate change, because dust has no boundaries. So, the United Nations General Assembly issued several resolutions and encouraged countries to actually collaborate to solve the problem. Also, the United Nations General Assembly tasked UNEP, UNCCD, and FAO to do a global assessment of sand and dust storm, and it was published in 2016. A major milestone actually in the region, now I've seen, is the establishment of the Regional Center on Sand and Dust Storm. Thank you for the Kingdom of Saudi Arabia. Thank you for the National Center for Meteorology. This is a very good starting point actually to tackle the problem. Also, I have seen or witnessed some on-the-ground action to actually mitigate the dust and sand storm, and this is really demonstrated by a project that was funded by by Kuwait to actually study the sand and dust storm in Iraq and Kuwait, and also do field level mitigation measures, and this was led by, or is led now by, Dr. Ali Dawsari, my dear colleague and friend. There were more political, there is now more political will. Is it, I don't understand how it works. Okay, it's mine. Can I have control on this, please? No? Next slide, please. Okay, so there is now more political will. Resolutions are coming from not only the United Nations General Assembly, but also last week a resolution on sand dust storm was agreed during the UNEA, which is the United Nations Environment Assembly that was held in Nairobi, but also resolutions from UNCCD COP and also from WMO and so on. So, actually, in order to solve the problem, you need an integrated regional approach. Integrated, that means that you need to address all the dimensions of sand and dust storm, not only the monitoring, measurement, and early warning, but also you need to have some transportation and climate dynamics studies. Also, you need to have monitoring, early warning, you need to have impact assessment, and most important of all is to have or to implement preventive and effective mitigation measures, and you have to manage the whole process in an integrated way and collaborative way between countries. So in other words, all these dimensions, the policy dimension, the science dimension, and the action dimension has to be in this master plan or regional program. It's also important to understand really the source, the hotspots, where the dust is coming from, the characteristics of it, but also what are the root causes. So I think the emphasis should be in identify the root causes of these episodes of sand and dust storms. In the Iraqi national program to combat the dust storm, we did this exact study. We did it by looking at the historical data, satellite imageries, and also meteorological data on visibility, because that's the only way that we could really measure, and also ground truthing. And we have identified 14 sites of sand and dust sources in Iraq, 2 of them only dust sources. The rest either only sand, and sand sources, as you know, they have local impact, so they don't travel a lot. The dust, they travel for long distance, and 8 of them are actually dust sand sources, and 4 sources are mixed between sand and dust, because sometimes, you know, the sand, when it travels, it becomes also dust source as it travels and deposit the heavy particulates. We need to understand the root causes so that we put the appropriate mitigation measures against this, and we have to tackle the problem from the source, from the root. Back in 2012, when it comes to monitoring observation, we had only like 2 or 3 aeronaut stations. Can you? This is Iraq study. As you can see, the red ones are the source of dust, and let me just see the colors. The red are the dust. The yellow is the sand, and the brown is the mixed. And you can see most of the sources in the south are actually mixed between sand and dust. And in the north and to the border of Syria, Al-Hammad, this is a major source of dust for the region, and it can travel long distance. So in the Iraqi study and the Iran study, we identified also the characteristics of these hotspots and the causes for these, and mostly it's land degradation, unsustainable water and land management, in some industrial areas, some quarries that really, or abandoned agricultural areas which actually left the soil very thin soil layer so that it is driven by the wind very quickly, which transports dust. These are the Aeronet stations in 2012, but now I think we have more of them in the region, more of Aeronet. I think in Saudi there are 5, in Emirates maybe there are 5 or 6 stations, in Oman 3. But the most important thing here is still we have gaps in the coverage of the Aeronet stations, especially in the source areas. For example, in Iraq we don't have any station. In Iran, only 1 dysfunctional station. In Syria, no station. In Jordan, maybe 1 station. So we need to really have a very good coverage of these stations so that we can study the transboundary effect of these dust sources. The region, actually, each country can be a source and can be a recipient of dust. So there is no country that can solve the problem alone. So it can be a source and it can be also a recipient. And this table just, an indicative table to show where the dust is coming from and where the dust is exported. In my previous presentations, I called it the dust trade balance, but maybe politically it's not correct. This one is actually where the dust goes and where the dust coming in. Also, in the within a regional context, I think there are capacities in the region at different subject, different levels, and so on. And I think we have to take advantage of these capacities. If you look at this table, you will find that some countries are very strong in monitoring, measurements, and research. Some countries are good in mitigation measures. Some countries are actually good in community-based approaches and so on and so forth. And I think we need to create this regional collaboration, and we have to define the region very well. In this slide, the region, as per the previous plan for regional sand and dust storm, it was, an expanded region of West Asia. In conclusion, there is a renewed opportunity to address the sand and dust storm problems through an integrated regional approach. Call it master plan, call it regional program, call it whatever. It needs to have all the elements together. Needs a long-term and sustained efforts by all countries affected and affecting. Focus on prevention to mitigate the sand and dust storm. Monitoring is good, but not enough. Early warning is good, but it's not enough. It doesn't solve the problem. So you need to solve it from the source, and you need to make sure that whatever you intervene, you make sure that you evaluate what are the impact of the interventions. So without really verifying, validating that what you have done has actually reduced the sand and dust storm, the activities and the program is not of value. So we need to make sure that we evaluate and we verify and we validate all the interventions, and we actually attribute the reduction of dust on these interventions. There is a need for concrete, broader coalition among metrology, all the sectors, metrology, environment, agriculture, and water authorities to address the problem. One agency, one sector cannot do that. Thank you very much.
Thank you very much, Dr. Majdi, and I'd like to thank all speakers for this opening session. Excellent set of talks. I hope you found them useful, helpful, and they've hopefully stimulated many questions in your minds and opening the door for further discussions and collaborations. We have 15 minutes now to gather some thoughts, and you have the chance to ask any questions for any of the panelists and hopefully start a discussion. So please, if you have any questions, let us know.
السلام عليكم. أنا المستشار قتيبة السعدون من وكالة البيئة مدير عام التنوع الأحيائي. أشكر السادة المحاضرين على العروض المميزة، وبدي أتوجه بالاستفسار إلى الدكتور علي الحمود من الكويت، الذي أوضح أن هناك تعاون بين الكويت والعراق في مجال متابعة منشأ العواصف الغبارية. والشيء الطيب والممتاز في هذا كنتيجة من هذه النتائج أنه تم تحديد مصدر لإحدى بؤر هذه العواصف الرملية. الاستفسار كما تعلمون أنه من أهم الوسائل لدرء عواصف الغبار هو معالجة مواقع المنشأ البيئية، فهل هناك بعض المقترحات أو المشاريع المشتركة لتشجير أو إنماء الغطاء النباتي أو أي إجراء من الإجراءات في الهندسة البيئية التي تضمن تغيير محتوى أو تركيب هذه البقعة بحيث لا تكون منشأ للمصادر الغبارية وتأثيرها على المناطق الأخرى، وإنما تكون رافدا زراعيا وبيئيا وتعمل فائدة على الجميع؟ شكرا جزيلا.
نعم، مشكور على السؤال. طبعا البقعة الموجودة في جنوب العراق هي إحدى البقع العشرة المؤثرة بشدة على شبه الجزيرة العربية، إحدى البقع العشرة، وهذه البقعة إحنا قاعد نراقبها في معهد الكويت للأبحاث العلمية على مدى 15 سنة، وصار فيها تغيير. وإحنا الحمد لله يعني الصندوق الكويتي للتنمية الاقتصادية العربية مول هذه الدراسة بمبلغ 3 مليون دينار لإعادة تأهيل هذه المنطقة، إحنا نسميها المنطقة الساخنة، لأن هذه مصدر من المصادر الرئيسية التي بسبب طبعا ريح الشمال وتؤثر كترانسباوندري، ما تأثر فقط على جنوب العراق اللي هي مدينة الناصرية، ولكن تصل إلى الكويت 250 كيلومتر مرورا جنوبا إلى الدمام، وصولا إلى قطر 1200 كيلومتر من هذه البقعة بالذات المنطقة الساخنة. وإحنا راقبناها بواسطة الأقمار الصناعية أولا على مدى 5 سنوات، وبعدين رحنا وزرنا هذه المنطقة on site بالفيلد، وخذينا منها عينات تراب لتحليلها في مختبراتنا، تحليلات الفيزيائية والكيميائية والراديولوجية. والآن إحنا basically من هذه المنطقة، لأن هي 1600 كيلومتر مربع، ولكن هذه المنطقة مثل ما نتصور الآن الربع الخالي بحجم الكبير، هناك بقع ساخنة هي المفروض اللي نركز عليها. فهذه المنطقة 1600 كيلومتر لما راقبناها عن طريق الأقمار الصناعية وبعدين عن طريق الفيلد فيزيت، لقينا داخل هذه المنطقة الكبيرة في بقعتين، واحدة في الشمال الوسط وواحدة في الجنوب الغرب، وهم هذول الرئيسيين المؤثرين. لذلك الآن بالتعاون مع طبعا اليونايتد نيشن UN هابيتات بدأنا في الآن كتابة بعض المقترحات بحيث أن إعادة تأهيلها بطرق حديثة وبالطرق الكونفنشنال. الطرق الكونفنشنال مثل مد البايبات، لأنها قريبة من نهر الفرات، مو بعيدة عن نهر الفرات، فمد البايبات وباستخدام البمبات، ولكن هذه الطريقة تقليدية ومكلفة. هناك طرق جديدة وحديثة مثل استخدام النانو ماتيريال، مثل استخدام البذور قبل الريني سيزنز عن طريق الطائرات، والبذور اللي هي الفطرية، ومن ثم مع المطر يبدأ الزراعة مرة أخرى. فالآن إن شاء الله قاعد نقوم فيها.
شكرا دكتور علي.
بداية مساء عليكم بالخير. عبد العزيز رشود، المؤسسة العامة للري. نشكر حقيقة القائمين على هذا المؤتمر. السؤال أو المداخلة هي أن المملكة العربية السعودية الآن لها جهود كبيرة في موضوع إعادة الغطاء النباتي والتشجير، أيضا لها دور في إقامة والمحافظة على المحميات الطبيعية، أيضا اللي هو التقليل وتقنين الرعي. السؤال هذه الجهود الجبارة اللي الآن تتم من خلال وزارة البيئة والمياه والزراعة، مدى تأثيرها على الأجواء والغبار وزحف الرمال والرياح والأتربة؟ فأعتقد أن هذه لها تأثيرات إيجابية. يا ريت من المختصين نسمع إيش تأثير ذلك. ويمكن لاحظنا السنة هذه يمكن قلت نسبة الأتربة والغبار. وشكرا.
Dr. Majdi, would you like to take this question? Dr. Abdul Majid, would you like to take the question, Dr. Abdul Majid? تفضل. Okay. Can we have the mic, please, to Mr. Jamal?
السلام عليكم، شكرا جزيلا على السؤال. الحقيقة يوم غدا إن شاء الله فيه جلسة حوارية ويتم التطرق لأسباب أو الجهود اللي بذلت من قبل وزارة البيئة بما فيها اللي هو الغطاء النباتي، وما سيتم إن شاء الله بالنسبة للجهود المتكاملة واللي أدت إلى يعني انحصار محدود وملحوظ الآن في العواصف الغبارية والرملية في المنطقة.
شكرا سيد جمعان.
السلام عليكم، معكم دكتورة سمد دباغ من الجامعة المستنصرية من العراق. فقط أحب أكد مثل ما قال دكتور علي من الكويت، أكو اتفاقية مع اليو UN Habitat مع وزارة البيئة والوزارات العراقية في عمل مشروع يخص التقليل من تأثير الدست سورسز في محافظة المثنى جنوب العراق. وإن شاء الله بدينا في الاستعداد لهذا الموضوع بعمل لجان من طبعا بالتعاون مع الميت أوفيس، بعمل لجان والشروع بهذا الموضوع بإذن الله. عندي مقترح أتمنى من الجميع يعني الأخذ به، مثل ما عندنا ساينوبتيك كود أو شفرة يعني ساينوبتيكية للعناصر الجوية، أتمنى أنه من كل المؤسسات الأرصاد الجوية أن تعمل أو تقوم بعمل شفرة للإير كواليتي تتضمن تراكيز الملوثات والإيروسول إندكس، الدست كونسنتريشن، لأنه من المهم جدا. ومثل ما استعرضت حضراتكم عندنا نقص كبير في الميجرمنت الحقيقية لهذه العناصر، فأعتقد هذا ضروري أنه يعني أجلس يعني كل 3 ساعات ولو أو ديلي على الأقل. شكرا جزيلا.
شكرا جزيلا. just تعقيب، أعتقد أن هذه مداخلة ممتازة وأنه I'll speak in English, I think there is translation. I think it's very important that we look at in this discussion at 2 things. Establishing the baseline, understanding where we are, and for this we need to understand the sources, we need to understand the meteorology. Remember, meteorology plays a major role in all of this, and understanding the role of meteorology, the wind patterns, the wind speed, the directions, but also the conditions for dust emissions from the source regions, like Dr. Ali explained in his comprehensive analysis, is very important. And it is a regional issue, and we need to have a framework of regional harmonization of the measurements, because we need to understand that the measurements have equivalent value. So the measurements you do in location X and location Y across the region have equivalent value in terms of quality. So we understand the difference between them is due to the environmental differences, not because of operation, calibration, or protocols. We have to harmonize the way we collect data. The quality assurance of the data has to be very importantly controlled and managed. So we share harmonized protocols across the region for measurement of PM10, of PM2.5, of all key meteorological factors. So this data is equivalent in terms of its value and its quality. And this means these researchers across the region can make the most of the interpretation and understanding of differences in the north, in the west, in the east, in the south. And this is really an important point for not collecting only data, validating the data, checking the data quality is a fundamental requirement for this. And on the bigger picture of sand and dust, we will need to think about 2 things. mitigation and adaptation. This is our resilience. Same as we talk about environment, climate resilience, also let's talk about dust and dust resilience. We need to understand mitigation of sources and adaptation. Inevitably, we have to adapt to some of this. In the urban areas and the greening solutions, we have to think of this on both parallels, in parallel, mitigation and adaptation. Thank you.
شكرا لكم الحقيقة. بس أود أن أول شيء يعني أقدم شكري لجميع المحاضرين في هذا المؤتمر الهام، والمواضيع التي ذكروها هي فعلا صلب موضوع مؤتمرنا هذا اليوم. ما أريد أن أذكر به زملائي حقيقة في دول مجلس التعاون الخليجي، ونحن تجمعنا لجنة اللي هي اللجنة الدائمة للأرصاد والمناخ في دول مجلس التعاون، أيضا كذلك هناك لجنة دائمة للأرصاد والمناخ في الجامعة العربية، وأيضا اجتماعات في المنظمة العالمية للأرصاد. موضوع الدست ستورم والعواصف الغبارية والرملية كان موضوع شائك من سنين. أشكر زميلي الدكتور عبد المجيد الحداد عندما ذكر، وهذه فعلا حقيقة، قال أنا 12 سنة مغيب عن هذا الموضوع، اليوم أظهر تاني. فكل ما أتمنى أن يعني أقوله في هذه الساعة المباركة وفي هذا المؤتمر، هذا هو الهدف من عقد مثل هذه المؤتمرات. هناك جهود موجودة في المنطقة ولكن للأسف مشتتة. ما ذكره اليوم الدكتور علي الحمود عندما ذكر بأن هناك آثار اقتصادية على البتروليوم فاكتوريز وتكلف 9 مليون دولار سنويا. هناك أيضا امباكت اللي هو السوشيال امباكت، التأثير الاجتماعي. هناك كثير من الامباكتس للدست ستورم والساند ستورم، الصحة كما ذكر الدكتور مجدي والدكاترة الأفاضل. إذا ما أريد قوله هو أنه اليوم نستغل هذه الفرصة مع وجود مركز إقليمي للعواصف الغبارية والرملية متخصص في المنطقة ومعترف من منظمة مثل المنظمة العالمية للأرصاد WMO، وهو رابع مركز على العالم، بأن تنضوي هذه الجهود جميعا تحت هذا المركز بإذن الله، حتى تكون هذه الجهود بارزة في المنطقة، ونحدد الأبحاث والدراسات والمخرجات من مثل هذه الأبحاث التي تفيد المنطقة بإذن الله. هذا ما أحببت يعني أن أقوله في هذه العجالة، مع تقديم الشكر مرة أخرى للمحاضرين جميعا. والدكتور رامي شكرا لكم.
شكرا جزيلا دكتور أيمن. I think we're out of time. We're ready for coffee. We have one more question before coffee break. So thank you.
عفوا تعليق بس نسيت أبلغ حضراتكم أنه احنا في صدد الاتفاق مع ناسا ايجنسي بخصوص عمل نصب محطة ايرونت في الجامعة الأمريكية في بغداد، بسبب أنه ردنا مع الجامعة المستنصرية، ولكن ناسا رفضت الاتفاق مع الجهات الحكومية العراقية وفضلت الجهات الغير حكومية. وإن شاء الله قريبا إن شاء الله نتوصل باتفاق، يعني باتفاق على نصب شبكة ايرونت في بغداد. شكرا جزيلا.
Thank you. Would like to, at the end of this session, I'd like to thank the chairman of the session, Dr. Al-Farra, and the dear panelists. Now, it gives me a great pleasure to invite His Excellency Engineer Jam'an Al-Qahtani, the Executive Director of the Sand and Dust Storm Warning Regional Center, to honor the chairman of the session and the panelists as well. Starting with Dr. Rami Al-Farra. Dr. Tariq Hussein. Dr. Hiba Safi. Dr. Ali Al-Hamoud. الدكتور ماجد الدوخي، مجدي الدوخي. And last but not least, Dr. Abdul Majid Haddad. Now we'll have a photo group.
Coffee break for 20 minutes and we will start at 11:30.
11:30?
Yes.
Okay.
20 minutes.
Okay. Now, thank you very much. Now we'll take a break for 20 minutes and we shall resume at 11:30. See you in 20 minutes. We have a coffee break outside and refreshments, so please feel free to have some light snacks and refreshments. We shall be back in 20 minutes. Thank you.
natural, guru. Una mágica, espiritual, natural, medicina. Una mágica, espiritual, natural, guru. Una mágica, espiritual, natural, medicina. Una mágica, espiritual, natural, guru. Una mágica, espiritual, natural, medicina. Una mágica, espiritual, natural, guru.
Assalamu alaikum. We'd like to invite everyone to make their way to the main auditorium. Our next session will be speaking about forecasting and mitigation of sand and dust storm, and it will be chaired by His Excellency Professor Alexander Bakalanov, and he will be introducing the panelists. Dr. Alexander, the floor is yours. Dr. Alexander. Dr. Alexander.
Dear distinguished, sir? Okay. Okay.
No, invite.
Start from here, then you come.
Dear distinguished guests and dear colleagues and participants, please, we have to start the next session. So we are focusing now on forecasting and mitigation of sun and dust storms. The invited speakers, please come to the presidium. Professor Slobodan Nikovic, Dr. Grigory Nikulin, and Dr. Takashi Maki, Dr. Mohammed Abdelkader, and Dr. Anna Vukovic, who are the invited speakers for this session. Sorry? Yeah, but maybe just good to wait and start sitting together. Yeah. Please start the first presentation.
from Baghdad. Baghdadi. Baghdad Alim.
I'm living in Baghdad. I'm not from Baghdad. I'm from Mosul.
Mosul. Okay.
Not of Iraq. But I was born in Baghdad and
today I'll start from my presentation on this session, and actually, for me, it's a bit new role to present, because we worked during last 10 years with WMO sun and dust storm warning advisory system development, and I was a focal point for that after Slobodan Nikovic, who was the main initiator of this program and was the focal point during many years before I came, and now it is Sara Bassart is the focal point from the Secretariat of WMO. And now I retired from WMO and returning to my professorship at the University of Copenhagen. So I will give a kind of combined presentation with our efforts with formerly WMO and also our recent studies with focus on combating and mitigation issues. So I will not stress one more what kind of importance for the sun and dust storms in Asia and in your region, first of all, and of course it is there are so many drivers for sun and dust, including land degradation and desertification, climate change, and also many artificial impact factors with anthropogenic activities. And of course, there is a growing evidence of frequency and intensity of sun and dust storms with climate change, and of course, negative impact, we already mentioned it, for health and for many other aspects, for agriculture, and energy sector, transport, and many aspects of urban areas and semi-arid regions economy. So of course, in this case, monitoring, forecasting, information and warning of sun and dust storms is extremely important. And it was one of the concerns of United Nations agencies and national authorities to integrate efforts and build a joint program for coordination of this work. Okay. And it is one of the reasons what the World Meteorological Organization initiates building of the WMO sun and dust storm warning advisory and assessment system. It was started in 2007. As I mentioned, Slobodan Nikovic, who is now joining this, was the first organizer of this program. And now it is growing further and further. And I'm happy also to see what the Gulf countries, Council countries, are actively involved in this process. And now I see great results of progress of last almost 10 years, what we tried to initiate this initiative of West Asia and Gulf countries to establish this center. And in 2018, we had first technical analysis of readiness of the Saudi Arabia to host such a center. And in 2022, it was the first event and official starting, and now we see what it's great progress of activities of the regional center in Saudi Arabia, and also what is important, many countries of the region are also deeply involved in this activity. Just I would like to make some suggestions for future development of the GCC SDS-WAS regional center and community, focusing not only on sun and dust storm forecasting, which was the main goal initially of the WMO SDS-WAS. But now, especially when the United Nations established a coalition for combating sun and dust storms, of course it is important to put efforts on the full spectrum of the problem and also including issues of mitigation and adaptation of sun and dust storm and combating sun and dust storms. This, I think, one of the important issues, and it is good what your new center could implement this part on the initial phase, not waiting when the forecasting system will be finalized, because it will be a much more efficient way and this system will be more user-friendly for different applications and for mitigation of sun and dust storms. So from this point of view, I think it is important additionally to meteorological service of Gulf countries, also involve environmental agencies and other agencies and communities, user community, including health, agriculture, transport, aviation, energy, etc. In this case, you can better forward your work meeting requirements from stakeholders. And of course, for global coordination, I think it is important to work closely with the United Nations Coalition for combating sun and dust storms. And of course, important also to increase observation system. This is one of the issues where you in this region need to improve and continue further with integration of observation data. And of course, for extending SDS-WAS initial goal, it is important to focus more on possible measures to reduce sun and dust storms in the region and also on a local scale. Oops. So this is what our vision, how to continue working. So we start from weather and sun and dust storm forecast and also now impact-based forecast and assessment. And further, it is necessary also go to risk management and also analyzing of resilience capacity of system and finally moving to mitigation actions. In this way, if to consider the structure of SDS-WAS, we can split two main streams. One, the first upper slide shows existing structure in this yellow color box of SDS-WAS, providing information for users for early warning and forecasting. And of course, it is important now to include also different sectors. And second direction of extension could be focusing on impact assessment and also mitigation strategy. So the first early warning and impact-based forecasting scheme is presented here, and what is important here is to consider different different type of impact on health, aviation, etc. Because threshold for concentrations and for warning are very different from sector to sector, and this part is need also to be included in future research and practical realization. Other important application is extension to impact assessment and mitigation policy. And here, of course, we need to analyze different scenarios and analyze also effectiveness of scenarios in economical and also impact-based assessment. If we provide some new mitigation scenario or policy, we can return back to the starting, this blue column with sources map and data, and run again modeling system for analyzing of effectiveness of the measures what you provided. So in 2016, UNEP, WMO, and UNCCD, and this global assessment of sun and dust storms provided this policy framework for mitigation of SDS. And green area are more in red color, you can see what's mostly covered by SDS was, but many policy issues are still outside of activities, and I think especially together with the coalition, it is important to move to this direction. And what kind of measures we can do to reduce anthropogenic dust emissions? First of all, it's covered by sustainable land development and water and landscape management. And of course, climate change mitigation and adaptation should be also one of the elements of these issues. And physical protection of CES is also important to reduce dusting, for example, windbreaks around urban areas and along roads and other infrastructure. From other side, it could be sand dune fixation with vegetation or some chemical substances. And of course, alignment of roads and removal obstacles to wind and load shaping, and building some green belts or fences to prevent dusting. And next step, I just would like maybe to focus more on current activities, what I'm doing now in Europe, together with Copenhagen University and Helsinki University and many other partners around the world, focusing on this Pan-Eurasian experiment multidisciplinary program where we consider interaction of anthropogenic impact, climate, and also atmospheric pollution with a strong focus on aerosols. And initially, the focus was on northern Arctic and boreal areas, and when Chinese colleagues included one more, you can see in this brown color line with dimension from north to south. And if you like, maybe we can consider also extension in vertical column, what is now is dashed line, for collaboration with Middle East and Gulf countries. So very welcome to join this program. And scientific plan for 20 years, I think, development of Pan-Eurasian experiment is published on the website of the program, and it is led by academician Marko Kulmala from Helsinki University and many colleagues others. And one of the modeling platform in this Pan-Eurasian experiment, it's EnviroHilla model, online couplet models what my team developed, and also it is multi-country involvement, and it is considered interaction, two-way interaction with online, fully online coupling of meteorological and aerosol and chemical processes in atmosphere. And one of the applications we also use for sun and dust and other type of aerosols. What is important, it is necessary to consider all processes in full chain of interactions. If we switch off one of the elements of this interaction between aerosols and other compounds of the Earth system, we can lose the processes and no chance to provide correctly the impact of aerosols. And also very important to very accurately forecast and describe the planetary boundary layer structure, which is the main elements for interaction in climate system. And just one example what I would like to show, it is WMO WIGNI working group for numerical experimentation. In one of the study, they analyzed different main models on global and regional scale. And this is one of the example when online coupling of direct effects of aerosols is included for episodes with a strong dust storm over Egypt. And on the upper slide, no feedbacks included. And when we are including feedbacks of dust, only direct effects, so it's only for radiation, it's modify the fluxes, solar radiation to surface and increase inhomogeneity of surface temperature, and it leads to increasing of 10-meter wind due to low-level jets within the boundary layer, and small increase of velocity leads much stronger increase of production of aerosols into the atmosphere because it's depend on power 3 on 10-meter wind speed. So it's interesting effect, but aerosols and dust impact on weather and boundary layer meteorological variables, and due to this change of meteorological variables, emission of dust for this dust storm increasing dramatically again. So this is a nice example of a joint two-way interaction between meteorological and chemical and aerosol processes. Returning to one of latest projects that we are realizing now, it is another type of dust storms. It's technogenic dust storms. It's mostly for mining and enrichment of mining or enterprises who save for long time technogenic dust. And it's provide also big problems, more local scale, of course, in comparison with, for example, Sahara dust, but it is also very important and impacting health and environment for this region. So this model what I presented is used for such studies, and we consider different scales from regional to urban scale, and finally up to local scale with obstacle solving, with CFD types, with runs or large area simulation, averaging. And here, this is the type of this technogenic dust sources from mining work and tailing dumps from mining enterprises. And here you can see what this dusting from the lowest picture. Unfortunately, pointer is not working. So, of course, it is much smaller, and but it is a good example for providing different effectiveness, analysis of effectiveness, different measures to reduce dusting. This is what we did in our modeling studies, and on example of Apatite town, it's in Russian Arctic, with this tailing dams, which are a big source of dusting for the city. We use here kind of downscaling with different scale of models, and finally use CFD type of model for analysis of different measures effectiveness for dusting. In the beginning, we start from analysis, because these tailing dams are usually elevated a bit around the landscape. So increasing of height of these dams, dusting also increased. And first we analyze how the height of tailing dam effect on efficiency of dusting and concentration in city. And here you can see what this higher damp, it's dramatically increasing the dusting. And next step, we analyze specific measures. For example, protecting fences or barriers, different type. Or, for example, here just consider a fence on dusting surface and analyze effectiveness of it. And as you can see from the right side, when we put this fence, its concentration is changing substantially. Not greatly, but at least it's efficient. And next step, we analyze height of this barrier and also analyze what is the most efficient with as you can see, it's changed not only dusting processes, but also flow structure is substantially changing here from the height of this. And also with the different height of the barrier, effectiveness of this measure for concentration is changing, and even high half a meter fence substantially reduce concentration. Increasing the height is not much affecting, but it's affecting when dust is growing behind the fence and the fence height became lower. This is the secondary effect. Other studies what we did with this tool, assessment of effectiveness of different barriers, putting on inflow beginning of the dusting part and in the end, and also analyze effectiveness of them and looking for optimal solution. I will not go into details because we already started a bit later, but who are interested, I just demonstrate this example as one of the possible tool for your center also work and looking for specific issues of mitigation and adaptation. Other study what we did, including green belts. It could be forest or other type of green areas protecting dusting, and also analyze different type of barriers. Just single line of trees and double and 3 and 4 barriers, and also analyze effectiveness of them. And also, will not go into details, but at least it is a good way to reduce, and such study could be used. And here you can see reducing of concentration of dust with this 4 option of green belts included, and correspondingly in distance how it's changing. Such example could be used, for example, for analysis of effectiveness of such fences close to roads, because, for example, in Saudi Arabia, as I know, roads sometimes simply not suitable for driving because of big piles of sand after dust storms. So just concluding, I just would like to stress what it is important to not stop on forecasting and just assessment. We need to think and analyze how to make situation better and provide different projections and mitigation scenarios to reduce dusting. And of course, seamless integrated modeling with two-way interactions between aerosols and meteorological variables are very useful tool. And again, because it's multi-scale processes, it is important to build this seamless downscaling to local scale, where we found what CFD tools and large eddy simulation type of models are a useful tool for analysis of effectiveness of such measures like fences or chemical fixation of dust surface or grass growing or green areas. So this what I also thought to recommend for the continuation of the center considering these issues. And of course, we are open for collaboration and continuing our work together. And just some references of publication what I mentioned it with many co-authors and colleagues. And also these 4 books what I mentioned it, and I suppose about compendium it will be, and a global assessment will be saying by my colleagues from UN agencies. And 2 last books are published in Russian about these technogenic dust storms and mitigation scenarios. Thank you very much for the attention. Okay, so let's go to the next speaker, and the next talk, Professor Slobodan Nikovic. As I mentioned it, one of the pioneers of SDS-WAS at WMO, a user-oriented modeling application for assessing mineral dust impacts.
Thank you. Okay, I would like to talk today about some applications for end users that could be outcome of dust modeling. So, do we have a remote? Okay. Okay, that's nice. So this is the title. As I said, I will talk a bit more today on some impacts and applications that are coming out from dust modeling. And you can see the list of my colleagues as well from the University of Belgrade and the HIDMET service in Serbia that participated in different ways. So there are a number of impacts that you can see how SDS and dust storms can affect the climate, health, transport, weather, and so on. And I'm sure that we already heard a number of impacts today, but also in the following presentations we will have more examples. Well, dust became really an international issue. When I was starting with the WMO, SDS was establishing as a project in WMO. It was already some experience, but this was one of the turning points when the program was recognized internationally. And I would also like to mention the Cost Indust project of European Union, where we, within this project, tried to get together the dust production institutions and end users. And it was very successful, one of the best in this period. 2 years ago, it stopped. Then the next example of international recognition is UN Secretary General regular report in which SDS is always mentioned and elaborated. And finally, not the last, but this is establishment of UN coalition to combat sand and dust storms. And later on you will hear more about that. So talking about process from research to applications, I would like just to mention, actually I am needing the microphone because that's too, if somebody can help me. I can just continue. So in this process, I would like just to mention that research starts with some particular idea, how to develop some application. Then that's important to validate this approach, and then you finally go to implementation if there is useful to the users. And this is the way that WMO SDS was following from the very beginning. So you start with the research, you look with one eye how to implement eventually or to use as output for some particular users. Okay. Hello. Okay. There is incoming WMO document which really talks about the assessment of SDS processes to provide services to users, and this is going to come by the end of the year sometimes. So the next, I would like just to mention dust modeling concept in general, what does it includes in our case. In Belgrade group, so we call it DREAM, Dust Regional Atmospheric Model, and this is the first regional operational model established in 1993, used in more than 20 countries or organizations. And in this kind of modeling, we use online linking atmospheric and dust within the same system. Interestingly, Richardson in 1922, he was the father of the concept of numerical weather prediction, mentioned in very early days that dust should be also a part of prognostic parameters in atmospheric models. So anyway, you can see here some images. This is dust process that is covered by our model. There are daily forecasts for a long time. We are part of the consortium in SDS was for NAMI node, for the Mediterranean African node. We use 8 particle sizes in the model, and we have a bit specific emission of particles using very detailed viscous sublayer processes close to the ground. Important component of our work on applications is the dust mineralogy. And together, one of authors is with us, Ana Vukovic, Vimic, of these global maps of 8 minerals. We just concluded that this is important input to our applications, so you can see what we published, and this data set is available to users. You can easily find it, a link, and download the data if you need something like that. Why mineralogy? Because it affects marine processes. It is important for health in different ways. It acts as an agent in ice nucleation, and you will see in my presentation later on that aviation also might suffer because of specific mineralogy. I will give you one of the examples, fish migration and dust. That's very recent publication of our colleagues from Spain, Rodriguez and the others, who made analysis of dust deposited over the ocean and the movement of skipjack tuna. So this reference indicates a strong correlation between the deposit of dust and the movement of this fish. I also found a reference for your region here in Saudi Arabia and surroundings, where this fish used to have some migration, the same type of the fish. So this could be a possible, how to say, same kind of process on both sides of the geography. Why to focus on mineralogy? Because of presence of iron oxide in dust, and you can see one of our maps that we produce on a global level, 1 by 1 kilometer, like our mineralogy. And here in this cartoon, you can see that mineralogy and iron solubility is changed because of the clouds, because of radiation, and finally separation of sizes. Once iron oxide becomes soluble, falling into the ocean, it might initiate the marine biological processes. So I will not go into these theoretical equations that we introduce into our dream model, but there are new equations for total iron, for free iron and soluble fraction of it. There are some examples of the testing of the model for some particular case where we had some data, observation data, and you can see on the bottom how we predicted for this specific period solubility. Solubility of iron means that you might expect more production of plankton, and this is the first level where fishes really are attracted by. Dust melting in avia turbines. I hope that this will be a good example for colleagues living in this part of the world. Let me see. Okay. So we analyzed the April 2015 dust storm. You can see how it was predicted by our model, and what was specific for it. This was a massive dust storm. Originated in Iraq. Flight operations at several airports in the region were totally stopped. Dust melted in several aircraft turbines, as you can see in this image on the bottom, and there was a multi-euro loss according to Rolls-Royce sources. So what we did in our analysis, we introduced a so-called melting index, because melting of dust very much depends on the structure of minerals inside. So in our case, and using our mineralogy, we were able to calculate what is the expected melted chance used by the model, and on the bottom on the right, you can see how we predicted in time and with respect with height the chance for melting, and it coincided very well with this particular event that happened in the region. So I will skip this one. This is the application that could be definitely used in operational manner, and we are seeking for some collaboration in this respect because our model is ready for this kind of running. Dust affects the atmospheric radiation. I have to check the time, I'm sorry. Okay, so within our experiments and in collaboration with the Spanish colleagues, we made a study of the impact of dust, how it affects the temperature in the region, in the Mediterranean region, and you can see what is the difference between the control run and 2-meter temperature when dust is introduced, affecting the calculation of temperature online in the model. So you can see that from our maps, reduction of the average AOD was almost 50% in some area of this geography, and also several degrees drop because of the presence of the dust in the region. There are another examples related to health that I would like to briefly mention. One is valley fever. I was searching if such illness is maybe relevant or existing in the region. I was unsuccessful at least, but I can just show you some maps for the southern part of the states, Arizona basically, where this dangerous valley fever exists. And interestingly to say that valley fever very much depends, spores that cause it, on soil mineralogy. So what we did in these experiments, we just matched the mineralogy from our mineralogical database and tried to predict the factor indicating the occurrence of valley fever. This was published reference, and I think there is also potential to run the model in an operational mode and that then predict for this particular region how to expect eventually the appearance of this sickness. And the last in my list of these applications, I would like to mention something about ice nucleation. Dust appears as a perfect ice nuclei. I also see that the last day there is a session on seeding, seedings of clouds eventually affected by dust, and it might be connected in some way. So in our case, the recipe to calculate the ice nucleation was to use the DREAM model, dust model, and concentration on it, the atmospheric model using the temperature and relative humidity, and then with a particular parameterization to calculate the concentration of ice nuclei, ice particles caused by dust. So in our case, we tested the model for a sequence of several days in Italy, and you can see rather good equivalence between the model in black, in color, with observations of radar and LiDAR in black. So this was for us a sign that we could be useful and successful in predicting this one. These are some just examples on the left. This is how we calculate the IN concentration, and this on the right is how the satellite see. And you can see that in a good part of this Mediterranean map, there is matching between two. It's not perfect, but all the patterns are more or less there. And related to ice nucleation problem, we made experiments for Air France accident with many deaths, more than 200 deaths in 2009. And here I can just indicate that we use our IN calculations from the model. This movie indicates that dust was transferred from the Sahara to the Atlantic Ocean, and this black dot is the location of the accident. So this published reference on the left down shows that this index that we calculated specifically for this analysis was calm all the time for a given height of about 10, 11 kilometers, but then it extremely increased just about the time of the accident. So our suggestion is that it might be, as also the analysis of the authorities showed that ice nucleation of Pitot tube was the cause of the problem for this particular case. I will stop with this one. I'm sorry if I was a bit longer, but that's all what I wanted to present.
Thank you. Okay, time is going fast, so we have to go further, and I hope that in the end we'll have time for discussion and questions. So the next presentation by Dr. Grigory Nikulin from Swedish Meteorological and Hydrological Institute, high-resolution climate projections to support adaptation planning in the Mashreq region. Please. And try to follow the time.
Okay, so good morning to all participants. And first of all, I want to say many thanks to the organizers of the conference for inviting me here. And also during last 2 days, we had a capacity building workshop focusing on analysis and impacts of sand and dust storm in the Arab region, co-organized by Economic and Social Commission for Western Asia, ESCWA, and the WMO Regional Center for Sand and Dust Storms. So it was 2 very intensive days with many presentations, discussions, and now I see all participants from these capacity building workshops are here at the conference. So now we will be moving a little bit to different time scales, to climate projections. So basically what we can say about sand and dust storm for next period from maybe about 20 up to 100 years. And here is a list of co-authors and contributors into these presentations. So basically it's from ESCWA and from SMHI. And if you look in generally now, so we see that there is a very high demand on regional and local climate change information from many different sectors, from very wide range of stakeholders worldwide. And because we're talking about regional and especially local scales, we always keep in mind that we need high-resolution climate information for this. And the global climate models, what we shortly call them GCMs, they are the main tool for producing future projections under a range of different climate scenarios. But somehow they still a little bit limited in resolution. So now we see that the resolution of global climate models is increasing, and some simulations already running at 15, 25 kilometers. For short periods, it can be even 10 kilometers. But if we talk about more complex Earth system models that include many different components of our climate, like the carbon cycle, dynamical vegetation, for example, interactive aerosol, these models are still, I would say, heavy to run at high resolution for long multi-decadal simulations. And they, on average, I would say, operate now at resolution about 100 kilometers. That may be not enough for regional climate information sometimes. And we very actively using regional climate downscaling just to complement, not to replace, but to complement global climate models and Earth system models. And for this, we're using dynamical downscaling with the regional climate models, and empirical statistical downscaling is shortly that also includes new machine learning methods. And on average, in generally, all regional climate downscaling is now coordinated by the Coordinated Regional Climate Downscaling Experiment. It's a World Climate Research Program project, has been running since 2009, so it's already 15 years, a long period. And Cortex defines 14 continental scale Cortex domains covering almost all populated areas worldwide. And actually the Middle East and North Africa, it's one of these 14 Cortex domains. So it's on the second globe from my side. And current resolution, what we recommend in Cortex, is to run regional climate simulations at about 25 or 10 kilometers. Of course, it depends on the size of different domains and also about capacity and resources of different modeling groups and different regions. Yeah, but of course, Cortex continental scale cannot fit to all needs. For example, running the MENA domain or the Africa Cortex domain at 10-kilometer resolution, it's still possible, but it's I would say it's still a heavy task because we need ensembles of simulations with many, many different models, regional models, downscaling different global models. And quite often we see that it's maybe much more flexible to establish smaller project-based domains. And one of these domains, so what we call now the MASHREC domain, was established within a series of projects. It was cooperation between ESCWA and SMHI. So here you can see this domain. So we're using a regional climate model HCLIM Aladan to run these simulations at 10-kilometer resolution for this domain. And we're running these simulations from 1961 to 2014 as a historical period with a prescribed forcing in greenhouse gases, aerosols. And then from 2015, we continue to run simulations under two scenarios. SSP 5 and 5, we can say it's high impact scenario, and SSP 245, middle impact scenario. So we are covering about maybe 50 variables, and many of them every hour, but also we provide most common variables like precipitation and temperature with a bias correction that it's really needed for impact modeling and different assessments of future climate changes. So it's something like a package of high-resolution climate data for the MASHREC region. And here it's a table with this ensemble. So we downscaled 6 global models from the latest generation of CMIP 6. And we basically try to select these models based on their climate sensitivity, because different models can provide you different response with the same forcing in greenhouse gases. So we just try to keep a range of climate sensitivities, taking model with the low climate sensitivity, with the middle, and with the high climate sensitivity. Even here we have some small bias to models with a high climate sensitivity. And one of models provide only forcing for downscaling under SSP 5 and 5 scenarios. Unfortunately, it's Japanese MRI. So we can say that the main ensemble consists of 6 GCMs downscaled by 1 regional climate models under 2 scenarios. And a subset of data from this ensemble has been made publicly available through RICAR portal. So everyone can go and access this data. And also this ensemble already has been used for many assessment of climate change, but mostly with focus on water resources, because it was the first idea about generating such kind of ensemble for the MASHREC region. And then we got a question, can we say something about future projections for sand and dust storm? And I actually was a little bit puzzled. So I just tried to look around what we can take from the latest generation of climate models and from climate modeling data currently available from global and regional climate models. And I found that basically it's not so much. From global climate models, we can take total AOD for dust aerosol, because several global models, they have also interactive aerosol model inbuilt. But usually they provide only monthly means, so we cannot focus on specific events like a sand and dust storm. And in regional climate modeling, we used a bit old approach, something like static climatology for aerosol, just with annual cycle. And basically this model we're using here also has this climatology for aerosol. So we just tried to look a little bit around, and then we decided to focus a little bit more on dynamical drivers of sun and dust storm. And for example, one specific proxy is a dust uplift potential. And it's very easy to calculate. It's not so complex because we need only 10-meter wind speed for these calculations, and then we need to define a threshold. But of course, the dust uplift potential is highly nonlinear because of the cubic function of the wind speed. So for this case, using, for example, even daily mean wind is not enough. So we really need to use sub-daily output from our models. And fortunately, we archived hourly wind speed at 10 meters for all simulations in the Marshall ensemble. So we used a threshold of 7 meters per second. As we found from literature, it's commonly used for bare soil. And then we calculated dust uplift potential for all grid points. It's even over the sea, yeah, but then of course we can put different filters for this. And here just one example of evaluation of dust uplift potential, when on the first upper slide we have the ERA 5 reanalysis from ECMWF as our reference, and then downscaling of another reanalysis, ERA interim by regional model, and downscaling of 6 GCMs. And basically, we can see that on average, we can conclude that our regional climate model underestimates the dust uplift potential in the central part of the Arabian Peninsula. But we also need to keep in mind that ERA 5 has resolution 0.25 degree, so it's about 25 kilometers, and our ensemble is 10 kilometers. So already there is some inconsistency in resolution. Yeah, and it's very difficult to find a good reference gridded data set for wind because it's very large uncertainties. But it's just for example. And if you're looking how we're using this ensemble to say something about future changes in temperature, for example, this plot showing what we can expect in 2041, 2060 with respect to 95, 2014. And the first row is basically showing the current climatology from 95 to 2014. And then projected climate change in the middle row. Under 2 scenarios, lower it's a high impact scenario, 5 and 5, and the upper 2 for 5. And basically we can see it's consistent picture, so we can expect warming across the region. And its warming is stronger in 5 and 5 scenarios, but also the last row shows you some kind of agreement. So basically how many simulations of 6 agree on an increase. And when you can see when that is green, so basically all simulations agree on an increase. But we know this because signal in temperature is very robust. But when we're moving to precipitation, it's already much more complex because future projected changes in precipitation have much larger uncertainties than for temperature. And here it's the same analysis, only we're taking temperature again for April, September, just basically it's spring and summer. But already here we can see some regional spots of changes in precipitation. For example, drier signal in Eastern Mediterranean, and this signal is getting stronger under the high impact scenario, 5 and 5. But agreement across different members of the ensemble, it's not already 100%. So we can see situations when maybe only 5 models of 6 can agree on and decrease or a decrease or an increase. And then we're moving to the same analysis for dust uplift potential. And dust uplift potential is based on wind. And we also know that for wind, uncertainties for future climate projections are very large. It's very difficult quite often to find a consistent signal across different global and regional climate models. But here we can see in any case that we can already identify a number of regional spots. For example, we can see that there is a decrease in the dust uplift potential in the northern part of the domain east of the Caspian Sea. So it's a little bit outside of the Mashrek domain, but in any case, and there is I would say, a good agreement across all members of the ensemble that dust uplift potential is going to decrease there. And then we can see, for example, another spot in the northern part of, and along the coast of the Persian Gulf, and also there is a decrease in the dust uplift potential. So basically it means this dynamical driver of the sun to dust storm going to be weaker accordingly to this ensemble. In some places we can see small spots with an increase Yeah, so I would say that it's a very different situation across the domain. It can be an increase or decrease, but on average we see that mostly it's a decrease in the dust uplift potential. And now I'm moving to my last slide with some summary. So we can see that dust uplift potential as a very, very simple dynamical proxy of sun and dust storm can be used to say something about future climate projections in the sun and dust storm. But of course, we need sub-daily wind to calculate this proxy. And it's not all models, especially global models, providing hourly wind, because it's a very huge data set if you running a simulation with a high resolution, for example, 25, 50 kilometers globally, and you need to archive hourly data. And of course, it's first example of our analysis, and it's seasonal means. And of course, seasonal means they can smooth many details. Yeah, so basically they're giving only very, very general pattern or general idea what can happen into the future. So of course now we are going to maybe run to more sophisticated analysis, for example, focusing on statistic of individual events. So, and maybe it can be some kind of indices, or we can say extreme indices describing duration and intensity of events. So for example, it can be the number of consecutive hours when the dust uplift potential is above 0. And of course, it would be very good, because I think the conference is a very good place to discuss it with the experts in this area, because for us, I'm coming from regional climate modeling. It's a very new topic, so I'm still learning about this. Yeah, so it would be very good if you have any comments, discussions, any suggestions, and so on. Thank you very much for your attention.
Thanks a lot. Really interesting study. And now we'll go into the next talk by Dr. Takashi Maki, Meteorological Research Institute from Japan. And Takashi is also chairman of ASEAN Regional Node.
Thank you very much, Chairman. And my name is Takashi Maki from Meteorological Research Institute. And thank you very much for the members of NCM for supporting my travel to Saudi Arabia. And today I'd like to show you about the current activity of SDS-WAS, ASEAN Node, and related activities. And this is the slide from Professor Alexander Bakranausa, and this is the brief history of SDS-WAS. And as he already shows the brief history, and I add the one event, important event. And last year, 2022, the establishment of the GCC node. And from 2007, the SDS was started to have 3 nodes, NAMUI and ASEAN and Pan American. And the important topic is that from 2014 and 2017, and the Regional Specialized Meteorological Center for Atmospheric Sand and Dust Storm Forecasting Center has established. The first one is the Barcelona Supercomputing Center, and the second one is the Beijing CMA Forecasting Center. And this slide shows how we have designation process of RFSMC ASDF. And the important topic is that this is the CMA case, and CMA and KMA and JMA has proceeded the technical report in which the report and the model forecasting ability is shown. And then the current WMO organization is different from at that time, but we have many processes, and RSG and SDS was SC and CAS. At that time, the Commission for Atmospheric Science, and also CBS, and finally the Congress and WMO. And now, today, I'd like to show you the ASEAN Node participant. Important feature of ASEAN Node is that we have 5 working groups. And this slide is the many participants contributing presentation. And regional steering group, and now I am the chair of the RSG. And also we have 5 working groups, and verification, and data sharing, data assimilation, and common portal site, and S2S, and climate change. And if the GCC node have started to enhance this activity, this is one example of our ASEAN node. And this is the data sharing working groups activities list. And now we are sharing the dust forecasting data. And then now we are planning to sharing the observation data. This is the observation data sharing CMA, KMA, and JMA. And also the common portal site activities. In this working group, and the activity is mainly dependent on the CMA, and they have many activities, not only in common portal site, but capacity building. I'd like to show you later some slides. And this is the verification working group. Now we collect the 6 centers prediction data, CMA, KMA, JMA, and also the ECMWF, and NSEP, and the FMI. And also we calculate the model ensemble mean. And this is the everyday's effort of each institute and the CMA. And also we developed a new working group, a data assimilation working group. Because the CMA, KMA, JMA has different data assimilation system, and now we exchange our knowledge and also the techniques and so on. And in the future, we'd like to develop such more sophisticated system. And this is the S2S and climate change working group. And this slide shows the Chinese activities. Now, only China have operational STS, longer dust prediction. And Korea already started, but they stopped this activity. It's unfortunately. And also, I'd like to show you the capacity building by CMA Beijing Center. And this is the first International Day of Combating Sand and Dust Storms, last July 12th. And at that time, the webinar has held by CMA and WMO and many experts. Unfortunately, I have to attend another meeting and I couldn't attend. And this is also the example of the cooperation platform Northeast Asia for joint prevention and control of sand and dust storm. Also, the meeting focused on the mitigation process of sand and dust storm. And also, this is the workshop on the United Nations Convention to combat desertification and sand and dust storm mitigation. And also, this is the workshop on the WMO and the Iran Meteorological Organization and Turkish State Meteorological Services. So many activities are held by CMA and the Beijing Center. And from now, I'd like to show you each country's activities, 6 countries: China, Korea, Japan, India, Mongolia, and Kazakhstan. Maybe the time is not enough, so I'd like to skip some slides. And this is the medium range forecast by CMA. And they extend the forecast range to up to 50 days. This process is important for the mitigation, sand and dust storm mitigation processes. And also, the CMA develops the chemical weather forecasting model, not only limited to air and dust, but also they calculate the air quality. Maybe the one important aspect is the air quality. So the CMA's activity is very, very remarkable. And also, our institute has developing such a regional model. And from now, I'd like to show you Korean activities. And they developed an ensemble-based dust prediction model in a seasonal or long-range forecasting system. We usually use the ensemble prediction system. And the KMA develops an ensemble system for alien dust prediction. And also, the KMA's important feature is that they are developing a machine learning system. And this is the one example of the adjusting the product of the model prediction. Using machine learning technique, they modifies the dust prediction result. And also, the KMA operates a geostationary satellite, GK2A, and they are now improving their retrieval system for, this is the standard RGB, and also they are now improving their retrieval system. And I'd like to show you Japanese activities. This is the operational observation system of JMA. We have 3 observational sites for monitoring the atmospheric AOD. And also, this slide shows the National Institute of Environmental Studies LiDAR network. They call them ADNet. The important feature of LiDAR is that they can monitoring the vertical profile continuously. So this is the very important network in ASEAN region. And also, I'd like to show JMA dust information. We provide satellite image and alien dust prediction result and surface observation result. And in our dust prediction model, we introduce a data assimilation system. In this system, we assimilate the Himawari geostationary satellite AOD data using 2D bar system from 4 years ago. The resolution of our model is almost about 40 kilometers. And I'd like to show you the climate prediction. And we now, MRI develops the system model called MRI ESM2. And in this system, we develop several components: atmosphere and ocean and sea ice and aerosol and atmospheric chemistry. And due to the lack of human resources, our agency used our system model for dust prediction. And so, and this is the climate. From now, I'd like to show you my research topic about how dust emission change in the climate scenario. And this is the dust emission change by our system model. And the left figure shows the Gobi Desert dust emission change from January to December, and also the annual mean. And the right 6 figure shows our dust emission change comparing with the current base period. Base period is 2015 to 2024. And seeing this figure, the lower panel shows the warming accelerated scenario, SSP 370 and 585. And seeing these two figures, from Central Asia to Gobi Desert, the dust emission is extremely increased in, this is March case, the early spring. Maybe this is because the snow decreasing in the global warming scenario, the dust emission increase. But totally, the dust emission amount is not changed due to the global warming. And this slide shows the GCC area for dust emission. And the left 6 figure shows the dust emission, and right 6 figure shows the friction velocity. This parameter is important in Gobi Desert analysis. But in this our simulation, the significant increase in dust emission in Central Asia in high emission scenario, SSP 370 and 585. And, but in this GCC area, the dust emission change little with warming scenarios. This is now preliminary result, and now I'd like to research in detail, and I hope to submit this paper. And also, I'd like to show Indian activities. And they have many observation monitoring systems in India. And not only meteorological agency, but also environmental agency. So they have also not only aerosol, but also air quality measurement system they have. And they have two modeling systems. The first one is SIRAM, developed by Finnish Meteorological Institute, and the other is WAFChem. And this is the flowchart of SIRAM, and this slide shows the WAFChem system. And Indian Meteorological Agency now operates such forecasting system. And I'd like to show you Mongolian activity. And maybe some pictures shown. And this is the main, this figure shows the observation network in Mongolia. And I'd like to show you next, this is the Tsoktobo site in Totri University. And many sites. And this is the list of observation sites in Mongolia. An important feature is that in Mongolia and Japan, China, Korea have also the cooperative activities and supporting to have an observation network. And also the KMA supported to operate model activities. They used ADAM for Mongolian Hydrological Institute, and they now using the research. Okay, thank you. And also Kazakhstan's activities. They operate SARAM model, as I have shown, and also that they use the first SARAM model for their own activities. And this is one example of the observation and model, and the model almost captures the event. And I'd like to summarize my presentation. And now ASEAN Node 6 countries are attended to this ASEAN Node. And important feature is that we established the 5 working groups. And in 5 working groups, we now research and operation combined. And China is the secretariat, and the effort of the Chinese is very large. And also that we hope to, this is my result, and I hope to cooperate with GCC node and ASEAN node, and also NAMI node and Pan American nodes. And thank you very much for attention.
Thank you very much, Dr. Maki, for very impressive presentation. And next speaker will be Dr. Mohammed Abdelkader, and talk about dust-air pollution interaction and emerging process for accurate dust forecast. Please.
Hello, everybody. First of all, thank you very much for this kind invitation and also very nice organization of the conference. Today, I would like to highlight something. First of all, this work has been done with other collaborators from different institutes, from Cyprus Institute, Max Planck Institute, and KAUST. Then I joined later National Center for Environmental Compliance. So today, I think Dr. Rami in the morning highlighted something very important, that pure dust is not toxic, all right? When it's emitted from the sources, it's not toxic. However, when it goes to chemical transformation during transport, this becomes toxic, and it has a different impact on the human health. However, here in this presentation, I would highlight how this mechanism is working and how it's represented in Earth system models, how the dust edging can affect the whole dust cycle in the Earth system model. So first of all, as you already see it before many times today about the dust cycle here. One important thing that is want to see here is the cloud, is the edging of the dust. When the dust is emitted from the source region to the right, to the dust layer, then it goes to chemical edging. This depends strongly on the chemical composition of the dust. Okay, because a different chemical composition of dust, it has different chemistry, and it eventually results in different compounds or salts. For instance, here, as we see here, dust, we can classify it in terms of some ions. These ions can be neutralized through thermodynamics when it reaches to thermodynamic equilibrium within the cloud, resulting in salts. This salts is completely interacting with the cloud droplets in different ways, depending on the composition here. And my colleagues in Max Planck here estimated this effect here to the top right here. It has 0.2 watt square meter at the top of the atmosphere in global scale, just because of the dust edging. And this is, I would say, a very strong impact for dust edging here. And if we see here the global scale of the global distribution of this, we can see it can affect dust everywhere. However, over Arabian Peninsula, we don't see much changes. So we need to look into more details in this here. So we used in our models here, we have a long-term evaluation over 13 years of Earth system model using complicated chemistry, using edging of dust and so on. And what we see here over Arabian Peninsula, we have a sustainable amount of sulfate is over Arabian Peninsula, which is very interesting because this, in addition to the dust, this means that this area, it has a very strong edging of dust. And this also have been shown with our colleagues from Max Planck when they do the Aqaba campaign along the Arabian Peninsula. They show also that from observation, from mass spectrometry observations, that most of the aerosol part is coming from sulfate, which agrees very well with very early studies that we have done before. And this is very interesting because we see here in this area we have a sustainable amount of dust suspended in the atmosphere. In addition to this, we have some sulfate or other pollution. This pollution not only from sources, but also can come from long-range transport, or even some of it's coming from stratosphere from troposphers. So what we see here on the right here, this is our air quality network stations over Saudi Arabia, which is maintained by our center, National Center for Environmental Compliance here. And what we see here is a fraction of the anthropogenic part of the PM 2.5. Interesting thing here, as we see, as mentioned by, I think, Dr. Ali in morning today, is the prevailing wind of the Shamal wind. Along this trajectory to the right of, or the eastern part of the Saudi Arabia, we see this, the contribution from anthropogenic part is around less than 10%. However, in the main cities, in eastern part, middle in Riyadh, and western part in Jeddah, we see this fraction is increasing up to 70%. So 70% of PM 2.5 is contributed to anthropogenic part, not only dust. And within the Saudi Arabia, we see it's mostly coming from dust. This indicates that there is a strong chemical edging of dust over this area. So can we see this effect, how it works? This is what we see here in the next video here. The blue lines or the cayenne, it shows the edged dust particles. However, the yellow lines, it shows only the pristine dust particles. So the blue lines or the blue contours shows how dust is edged, the level of edging of dust. And we can see here over Saudi Arabia or Arabian Peninsula, it's a lot of edging of dust. And this is happening because of the suspension of dust and because of also air pollution from different sources here. And this indicates how this can affect dust forecast in the center here if this effect is not accounted. So how we can calculate this? Just for simplification, I just show the dust particles is suspended in an atmosphere. Pure dust particle is surrounded by acids, HCl, H2SO4, or HNO3. All of them are coming only from air pollution. And once this acids condense on the dust particles, this dust particles, it changes completely in microphysical properties. So it can start now to condense water vapor on dust particles. In morning today, we see that dust particle, as Professor Sullivan said, pure dust particle is very efficient ice nuclei. However, when it comes aged and it starts to absorb water, it becomes very efficient CCN. So this is a competing processes between ice nuclei and CCN, and is controlled by the level of aging of dust. And here, this is how we can estimate the level of aging of dust here. And what I want to highlight here is we can describe it by 4 independent variables: temperature and pressure. This is okay. And then the particle size. And then the third one is the accommodation coefficient. The accommodation coefficient is how much the dust particle can hold air pollution. And this is a limiting factor here because this can control the whole system. In our simulation, we estimated the accommodation coefficient based on the lab measurement that is done in Max Planck Institute and use it for global models. However, in our region, we don't have observation for this, for accommodation coefficient. Some of the experiments was trying to measure it here. However, I think if we need to have more accurate this, we need to make more observation for such kind of parameters here. And then we used a very detailed setup of the model. So we have full complete chemistry, we have full complete of microphysics. The dust is chemically active in 2 ways. First of all, it's can active during transport, and also can be chemically active within cloud droplets. So within cloud droplet, dust can be neutralized and with completely independent chemistry from the transport chemistry. And this is a very complicated setup that can show how this can affect the climate later on. And we use the setup here for 2 different cases. The first case is over Eastern Mediterranean. The other case is over the transatlantic transport. So what we see here, what you see here is this is a dust outflow, what you see from MODIS images. And below we see the model, the synoptic condition here, that we have a dust front, and during this dust front that's coming from Sahara, there's also a transport of air pollution from Europe. And this shows a very interesting situation where the dust and air pollution is coming together in same place, and we can see now how this interacting and how this affects the accuracy of the prediction here. We make some comparison here with Aeronet. We see now the model is nicely capturing the optical depths. This includes dust edging effects here, in what we see here. And also from the station in the Cyprus, we can see from LiDAR the extinction of the dust particles here. And this is only for dust. So we get the model, and for the LiDAR, ground-based LiDAR, and we see that the model and LiDAR, they capturing the dust layer pretty well. However, in lower elevation, while the LiDAR is not working perfectly due to higher load of sea salt and so on, within the bound layer, we cannot resolve the extinction close to the surface. And now we want to understand how the dust edging affects the prediction here. So we did 2 simulations, one including dust edging, and one without dust edging. Most of the models in global models, they don't account for dust edging. Some of them, they account for it, but in a very parameterized way, which means it just puts a fraction of the dust that is could be edged. And what we can see here also, we compare it with a spaceborne LiDAR system from Calypso data on board of Calibo satellite. We can see here nicely the satellite track on the black line is overlying the dust storm. And we get the modeling here, and we see over, sorry, we don't have a pointer. But we can see here the model, and the Calebo can resolve this vertical structure of the dust outflow very nicely here. And two important things here that we can see in the lower figure, the classification of a Calebo about dust was mixed with air pollution and pure dust. And we see over the Mediterranean in the brown color, it's mostly polluted dust, and over Sahara, it's mostly is coming from pure dust, which also agreed pretty well with the model. And now, when we do the sensitivity tests here, we get very interesting results. First of all, when we include dust, as I said before, it becomes a very active CCN. And this results in very, very high efficient removal of dust because of the edging. This is what we see here, is the blue part of the deposition rate. This is the deposition rate because of interaction with the cloud. And this, you see, if we doesn't include edging, this significantly decreased almost to 1/3 of the deposition rate of the dust. The same we see at either in Athens, in our National Observatory of Athens Station, or in Katibak in Cyprus. So both of them, they agree that dust edging has very strong impact on removal because of activation for below cloud processes. The same thing, actually, we did it for the transatlantic transport case, exactly the same. We see also that the dust is, the vertical structure of the dust is nicely captured, and the same classification we see the same, and we get exactly the same results at the Caribbean side. The deposition of the dust is almost 3 times different if we don't include dust edging. And this is one of the issues that the people was trying, what is the reason of different dust loading over the Caribbean. One of them was the dust edging during the transport. So we did the same test here to test how this mechanism is working. And to the left here, we see the dust parting for the non-edging, the effect of edging here. And the right one is showing the AUD. The interesting part, what we see here is controversially that in some places we have the dust edging is decreasing. However, the optical depth is almost increasing on the other side. This is, it shouldn't work like that, because if we have less dust in the atmosphere, you should have less AOD in the atmosphere. But how this comes here? From this, we found that there's 2 competing effects of the dust edging. The direct one, which dust is become edged, absorbs more water, the dust particle increase in size. This results in the higher sedimentation of the dust. And this is the direct effect for the larger particle of the dust. However, when you increase also the particle size, you increase the scattering cross-section, and this increases the optical scattering of the sunlight. And this is what we see here as dust edging direct effect and dust edging indirect effect. So lastly, we just show how this mechanism is working in the air system model. This schematic represents this process from emission to transport and then to deposition. This is what most of the model resolved. When you get the transport, based on sedimentation, goes to deposition directly, or you go through cloud processes, and this is scavenging. However, when you introduce edging in this in the process, this changes directly the optical size through optical properties through the size distribution, and also it changes the efficiency of the scavenging or activation of the dust particles within the cloud. Both of them eventually goes to the radiation and changing to the radiative balance, and this is what we see before in the first slide. In global scale, it has almost 0.2 watt per square meter on top of the atmosphere. So eventually, what I want to highlight here is 2 things. First, actually, dust edging is an important process that can control completely the dust cycle. It can impact the cloud formation, especially here if we are interested in cloud seeding. This process can also have a contribution. It could increase or decrease, we don't know. It needs to be included or studied separately to see this affects how it works with the cloud seeding program. We saw also that the dust aging effect has almost 3 times, impact of 3 times on dust deposition, which I would say it's a huge impact for such a process. Thank you.
Very, very important and nice study. And final talk for this session is by Ana Vukovic, Dr. Ana Vukovic from Belgrade University, a summary of current challenges of dust numerical modeling, both in climate and forecast. Please, Ana.
Okay.
Chair of the NAMI node of SDS was the new chair.
Thank you very much. I work at the Faculty of Agriculture at University of Belgrade, but I'm a meteorologist, and my expertise in numerical modeling and also climate change and so on. But also the main reason I'm here, one of the main reasons is actually that I'm now the chair of the regional steering group of the NAMI node of the SDS was. So my presentation will actually be a short summary of the current challenges in numerical modeling, which also need to hear the wider audience, the policymakers and also the soil scientists and so on, because it's important for further improvements. We need dust numerical modeling because besides using them in early warning systems, we can also use them to better understand the interactions with different sectors. For example, two-way interactions with agriculture, because agriculture is producing dust sources but also is affected by dust. Also impacts on health, traffic, energy supply, impact on natural environment, and so on. You see many, many results regarding these interactions. Then we can use models to understand the impact area of dust sources, which can help us to prioritize the areas which are urgent to mitigate regarding the decision-making in mitigation of dust sources. Then we can use the models in understanding the role of dust in the climate system. There will never be enough observations to cover this knowledge, so the use of numerical models is essential. And some of these useful things that could be done with the dust numerical models are in the domain of relatively short-term simulations, and some of them are in the domain of climate scale modeling. But why dust modeling is specific and it's hard to actually model events related to dust is that dust originate airborne dust from the scales which are relatively local and depend on the local conditions. Near surface wind velocities and the land characteristics. And these injected dust from these source areas can have impacts far, far away, which means that we need to have good representation on local scales to be able in the model to uplift the dust and transport it far away. So this is very, very challenging in dust modeling because this means you need to have high resolution, but also you need to have a large domain. There is actually roughly said two groups of the dust models. The ones where is dust online coupled with the weather and climate models, and the ones which use offline coupling, meaning that they receive input from meteorological models and do just dust transport. The research priorities differ depending which domain your research is focused on global domain, on wider regional domain, or on local scales. When you work on the larger scales, current focuses is to make good reanalysis fields of dust, then to catch all the climatological regional sources and seasonal sources. It's not that important to catch all local small-scale hotspots, but it is important to have good, to actually bring more and more parameterizations of the interaction of the dust with the climate system components. But when you go to higher resolutions and to local scales, when it's much smaller domain, your priorities in your research change. You need to have good representation of sources, good representation of collective activity, and so on. We are not able to do both, to have high resolution large domain, because even in numerical weather forecast, we didn't reach as a humanity that ability in our computer resources. But what is I actually want to highlight here, what is already seen by in the GCC mode is actually they produce for a relatively large domain high resolution forecasts with nested even 1 kilometer resolution for specific areas. They work in non-hydrostatic mode, which is very, very rare on such large domains. Sensitivity of dust numerical models, there are many sensitivities, but highest sensitivity is in parameterization of the dust sources. On the distribution, variability, and characteristics, then there is also a problem with representation of the surface winds, which are essential to lift up dust in the model, and we need some upgrades of the surface emission parameterization. These are current priorities, but in previous presentation we also heard there is an issue also with better deposition parameterization. What I will talk here, I will focus here on the sourcing and the surface winds as the main problems which could impact the limited performance of the models, and there is a great capacity also in GCC node in this region to maybe resolve these issues, because in my experience and of my colleagues, here is somehow better coordinated work and joint collaboration of the soil scientists and numerical modelers, and some issues can be resolved with this kind of collaboration, which is rare actually in the world. Users of the model products should be aware what are the inputs of the model products. Usually somebody sees the right image and says, okay, this is areas affected by the dust, but not considering what are the input data of this model. Input data are usually such maps which are developed according to the GNU reference, which actually recognize only the major dust sources. And there is no way your model will show dust events if it does not have properly input for all the dust source areas. The users should be aware what are the inputs for the models. It doesn't mean that this model doesn't work, it just doesn't have good input data to perform well in some regions. The UNCCT Global Sand and Dust Storms source-based map actually is developed using land surface information and soil data, which are globally available, then land cover data, also soil condition data like moisture and temperature, and we can see on the left side the surfaces which are always exposed to the dust emissions, always bare, and represent the dust sources during the whole year. And on the others, on the right side there, this is a map when we include also the seasonal sources and the sources which appear only during some extreme events, for example droughts or heat waves in cold regions when soil is not frozen. So the reality from month to month, from year to year, is somewhere between these two pictures. Actually one of the significant conclusions using the results of this map is the permanent sources of dust occupy 21.6 of the land surface Earth of the Earth land area, and 7.7% actually can produce severe dust storms. If we include all changeable, meaning seasonal and occasional dust sources, we can see the dust emission can happen from 42.8% of the land area, and 13.2% of the land area of the world can produce severe dust storms. Which tells us that this is actually a global problem, confirms this fact, but maybe not recognized as such in the world. You can see on the other map how the new seasonal sources appear, the high latitude dust sources, which is also confirmed recently by the observations. On the left is actually in blue the variable sources, and in yellow to red the permanent sources, depending on their capacity to emit. And on the other is the type of sources, is the cropland, the graded grassland, and so on. The representation of the surface winds is also important. You can see on this on the left side that we have course about 10 kilometer resolution model, how it performs. This is vertical cross sections of the dust storm, one can see of Tehran dust storm, and on the right side when it's 4 times higher resolution. And okay, the convective activity is not possible in the first case, but is well represented in the other case. But I want to draw your attention to something. When we have not well adjusted the resolution to of the model to the event we want to simulate, we can have also totally false signal. In this first case, the dust came from the east, and actually it came from the south, as observations show and simulation. So it also could be dangerous not to apply a proper resolution of the model if you want to have good warnings. But this is a problem when you have climate simulations and because of the computing time demanding. What is current actually challenges in parameterizing dust sources? I want to warn that soil texture data are missing in the areas where dried lake beds, the dried river, the retrieved glaciers. There is no data on soil texture there, and there will be no emission there in the models. We would like to also to include the soil structure data, maybe using some soil organic carbon contact, because with better structure they will emit less. And then we would like to update the dependence of soil moisture, because now we are aware that also in wetter regions the emissions are possible, and also dependence on the soil temperature, because now because of the heat waves we have a problem that some soils in the cold regions are not frozen and emit dust. This is very important. The modelers are finding very difficult to produce the products needed for the wider community, because we don't have the standardization of the products. Surface concentration is different among the models because they're using different PMs. Some models are working even to PM300 domain of particle sizes, some of PM10, some of PM30, and we cannot compare their results. So it's difficult to communicate or to establish some multimodal ensemble. Regarding the climate system interactions, dust cycle interacts with all climate system cycles, and there are many interactions, but recent publication says that it's somewhat higher probability that global dust has cooling effect on our climate under climate changing conditions, but on regional scales it can have much warming impact. For example, when it deposits on the snow, it can change its albedo, accelerate its melting, and it is a problem for water ability in the regions which depend, like in Himalayas, or I don't know, in Iceland we have this problem, and so on. So the problem in climate projections remains. dust sources in the future. This is the last slide. What is beside the product standardization, we want to have standards like in weather forecast. It is also important to decide on terminology. For example, what is the SDS definition? Does it also, when we talk of sand and dust storms, do we also consider blowing dust events? Or do we also consider long-range transport dust, or just some severe events with dust mainly near ground? Then we need a strict definition, what is SDS source? Is it related only to land surface characteristics? Then we get also many questions. Do you take into account anthropogenic sources? For modelers, is important the exposure of land surface to wind erosion. We do not distinguish anthropogenic and natural. This is diagnostics for us. But switching on and off some sources, we can assess what is the contribution, for example, of anthropogenic sources. And there are papers estimating that some dust storm events actually would be 50% with 50% less concentration if there was no agricultural sources near cities. So it can be, modelers just need terminology to communicate with users and policymakers better. And we would like at the end also to decide on the terminology officially on what is sensitivity, exposure, vulnerability, and risks. Do we take the IPCC vocabulary or we have our own? Because the products differ if we talk about sensitivity, exposure, vulnerability, or if we take these terms for wrong. Thank you.
Thank you very much. Well, now we have a bit limited time for discussion, but at least I suppose that it's important to hear some questions from your side.
Thank you very much. My question to Dr. Abdel Qadir. You've been talking your work on aging dust, right? And air pollution. How is the effect of dust aging on air pollution, and what's the application of your research comparing the air pollution and dust carrying particulate or microorganism causing air pollution? Thank you.
Okay, thank you very much for the question, a nice question. So first of all, the dust aging, it has, as I told you, it has one effect on the dust side, but from the other effect is the effect on the air pollution itself. So the dust is acting as a cleaner for the atmosphere because it absorbs air pollution from atmosphere and deposits it. So this has a different effect that we discussed today. For the direct application of it, I think it goes again with, as Dr. Rami mentioned in the morning, about the health impacts, especially the toxicity of the dust particles. Because the dust particle, the pure dust particle is not toxic. Once it's aged, is toxic. So to understand these effects, you have to, first of all, include these effects in the modeling part, and this you link it directly to the health impact studies. And otherwise, I don't see that you cannot do it without including these effects. Does it answer your question?
More questions? Yes, please.
I am.
Okay, thank you, Alexander. Just my question for Gregory Nicolin.
For precipitation, he mentioned that he take it from September to April. Sorry, it's opposite, April to September. And this is not the rain season. The rain season is coming usually from September to April. It's opposite. Thank you.
Yeah, it's a good question because yes, the period was from April to September, but basically just focusing on spring and summer sun and dust storm over the Arabian Peninsula. So there was no any specific case just focusing on this season. It's more like example. But of course, we can have an analysis for different seasons, focusing on a rainy season in different parts of the domain, because I think it's also not the same across the domain. Yeah, so basically it just was an example.
More questions? Yes, please.
Okay. I'm Hashim Sharba from Syria Meteorological Department. First of all, I would like to share Professor Gregory to sharing my thanks to the Kingdom of Saudi Arabia for hosting such a valuable and informative back-to-back workshop. Many thanks also to ESCWA and WMO. Actually, I have two questions. First question to Professor Gregory. My question is, in order to improve the climatic modeling in Mashriq domain, what do you recommend? Increasing spatial resolution or extending the domain with same resolution, or adding more factors, complicated factors to the process? My second question is to Professor Nechkovich or Professor Kaana. I would ask to nowcasting with dust emission. Is it possible to improve such model which related to emission of dust, which is not dynamic? It could be focusing on emitting of dust, like flash flooding models, for example. Is it possible or no? Thank you very much.
Okay, so maybe I can start with the first question, yeah, about...
Yeah, the first question was to whom?
To me, I think. Yeah? Yeah. It was to me.
Yes,
yes. Yeah, so basically question about resolution, domain size, and complexity of climate models. So of course, if you take a perfect case, we want to have everything in one package. We want to have a higher resolution, perfect maybe just to have something about 2-3 kilometers for convective permitting scales, when we can resolve small scale features like huboops, for example. Then of course we need to have more components in our regional models. So sometimes we call it regional Earth system models, including, for example, interactive aerosol, dynamical vegetation. Yeah, and about size of domain, of course, if you make model more and more complex and moving to higher and higher resolution, it's very difficult to run this model for a large domain. So I would still say that the size of domain should be somehow limited, or if you move into really high resolution, even smaller, focusing maybe on small subregions. So of course it's a perfect case, but of course we always need to think what we currently have and what is our capability to produce new climate simulations with different resolutions and different complexity. But in any case, we see a tendency for all climate models in different activities that the resolution is increasing and the complexity of models is also getting more and more stronger, we can say.
And Slobodan, please, we have lack of time, so just quickly.
Hello? Okay. I would like to say that nowcasting as an approach is usual in numerical weather, in weather prediction, better to say, and it covers the period of several hours. Usually you use the satellite or radar data just to extrapolate the status of the atmospheric system and try to extrapolate within several hours from now. Your question was, if I well understand, is it possible something like that to do with the dust? I would say that I think yes, if somehow your modeling system is online. So this means that the concentration is driven every time step by the atmospheric model, even with relatively large errors that you can expect within a few hours before the full dynamic starts to work. Still, my opinion is that you can get some insight or some indication about the dust process on a very short time scale.
Okay, thank you for all questions. Sorry, we have to finalize the section, so just a few words to conclude. Just
small comment, maybe.
Okay, please. Go ahead.
I just wanted to add something that we didn't mention. There is somehow still poor use of the radars in dust nowcasting. There are actually indications that dual polarized radars are very useful tool to use in the nowcasting of the dust. For long-term transport, okay, you can follow satellite data regularly and the dust forecast, but in short-term transport, there is a very big use of the high-resolution models which can, because then you can catch also the severe dust storms which occur usually below the clouds. And sometimes they are not visible by the satellite data, but then radars can catch them as they're approaching.
Okay, Anna, I think maybe just during the coffee break, the details you can discuss. Just to conclude the section, I would like to stress what really great progress in modeling for forecasting is provided in many presentations, and also what is nice, what impact-based forecast is quite actively used, which is very important for be closer to end users and applications for different sectors, and also what is progressing with climate interaction, several presentations following. Concerning the second part of the section, focus for mitigation studies, yes, they are presented, I see, and going forward, but not much yet. So I think it is really need to be turned to this issue, especially also to adjust models to make suitable for mitigation analysis. And others think what local scale and high resolution modeling is also needed specifically for such events like Habub, which are important in this region, and of course again for mitigation to analyze effectiveness of different measures. There we need much more high resolution and accurate simulations. Thank you very much for the attention, and now coffee break, please.
Thank you. Thank you, Dr. Alexander. And I'd like to thank our dear panelists. Thank you, and Hvala. Now I'd like to invite His Excellency Dr. Jam'an Al-Gahtani, the Executive Director of the Sand and Dust Storm Warning Regional Center, to honor the speakers, starting with Dr. Alexander Bakalanov. Professor Slobodan Nokovic. Stay, my coast. Okay. Dr. Grigori Nakulin. Dr. Takashi Maki. Dr. Muhammad Abdul Qadir. And last but not least, Dr. Anna Vukovic. Now I'd like to have all the speakers, esteemed speakers, to have a photo group. Please, if you can come forward to have a photo group with His Excellency Dr. Jaman Qahtani. Can you please come forward to have a... Thank you very much. Now we will be moving to the third session of the day, and that would be the last session of the day. It's titled Monitoring and Prediction Technologies. I would like to invite Professor Jean Sker to chair the session. Please, Professor Jean, please to the stage. وين دكتور جي؟ Dr. Jean, please to the stage.
Let's have 5 minutes break only.
Just to prepare for the session, we'll have a break for 5 minutes and we shall be back. We apologize for the delay.
يعني مو مشكلة.
Assalamu alaikum. Please make your way to the main auditorium. We'll start our last session of the day with Dr. Okay, Siar. With Dr. Jean Siar. He will be speaking to us. The title of the session is Monitoring and Prediction Technologies. He will take over now and invite the panelists to the stage. Dr. Jean, the floor is yours.
Hello, because I think people are still at the coffee, I would like to check that the 4 colleagues, part of these sessions, are in the room. I invite them at the stage. Dr. Shandan Charangi, Dr. Ishaq Sulaiman, Dr. Reem Al-Shamari, and Dr. Ahmed Saman. Please, if you are in the room, good. And please take a seat. You are one of the panelists? Yes. Okay, nice to meet you. Thank you for being here. Have a seat, please. Hello. So I will start my presentation, and hopefully it will bring more people inside the room. I would like first to thank the National Center for Meteorology, especially Dr. Ala, who has been working very hard to organize this great conference and supporting all these great speakers for presenting their work here. My presentation will be about new technologies for monitoring and better predicting sun and dust storm in the region. When I was asked Dr. Ala to think of a possible title, I thought of this because I'm a geek of technologies. So I will be happy to present you some of the latest developments that are available currently in the scientific world to better characterize sun and dust storms. So my name is Jean Siar. I'm the director of the Climate Atmosphere Research Center at the Cyprus Institute. This center was established 4 years ago by the European Commission to develop a regional center in the Eastern Mediterranean, but also for the Middle East, to address issues on air pollution and climate change. So we have received, in this respect, support from Europe, but also from the government of Cyprus to establish our center. So this center now has been growing as about 100 research staff. I will present you my presentation, if I can play my slides. Good. So I will give you a brief introduction of what will be my presentation for half an hour. I will, first of all, mention about the challenges that we have in monitoring and predicting PM from dust, new technology tools and methods to better monitor the dust, new models, new opportunities in the region, and conclusions and take-home messages. Right, one of the first challenges to monitor dust in the air is to discriminate dust from every PM sources. And as greatly illustrated by many of my colleagues this morning, what you have in the air is many sources of natural and human-made aerosols and activities, and this will be mixed, this will be transported over long distances. So how we can recognize what we breathe, that is dust, that is pollution, that's the first challenge. The other challenge to monitor in real-time dust is that this type of events is highly dynamic, as shown here on this picture. And then, obviously, if you want to get an early warning system, it must be providing real-time information relevant to several stakeholders. You need to inform the public and policymakers, and so for many of the domains that are illustrated here. So the second challenge is here not just to discriminate dust from everything else, but to provide a real-time information. The third challenge is about providing dense observations. This satellite picture on the left is the aerosol optical depth that shows that you have a lot of aerosols in the air, especially around desert, like the Arabian Desert, the Saharan Desert, much less in Europe. However, if you look, the monitoring capacity is implemented right now, and this is the UNEP network that is with automatic LiDARs and state-of-the-art ceilometers, more than almost 300 stations covering 22 countries in Europe. You see that they are doing a great job over Europe, where there is not that much of aerosols, but not that much in the region. So where we need the most information about aerosols. So there is currently a big gap of observations, and this is the third challenge. Now, how we can fill these gaps with new technologies? There are, in the past, well-established methods to monitor the dust in aerosols. Is typically using filter sampling. It's like your vacuum cleaner. You just throw air on your filter, and the filter is collected and then sent to laboratory for chemical analysis of a couple of chemical species. You will be able to reconstruct the mass, so you'll be able, through this chemical analysis, to understand all different components of aerosols. And then you will use some typical equations that are from Earth crystal chemical composition to derive your dust concentrations. And this is the first and the most used, let's say, reference methods to measure dust in the air. Now, there is new online technologies which are, as showed you before, needed for informing stakeholders. One example is a new technology that we are running now for a year in Cyprus that's called Aerodust. That is a technology that measures aerosols above 1 micrometer. And Professor Rami Afara showed this morning that basically if you look at big particles in the region, it's mostly dust. So this has a kind of imaging recognition system with AI that can count aerosols, that can count their size, that can look at their shape, and then go back to information like mass concentrations. And this type of technology is very interesting because it's quite cost-effective. It's a few thousands of US dollars, and then has the potential to be implemented in large networks. Other technologies that have been using here is relying on a property that is typical for dust, that is absorbing. Dust is scattering the light, but it's also absorbing the light through specific chemical species which are hematite and goethite, which are iron-based particles. And if you are using this type of instruments and you enrich the coarse fraction, and you are able to derive a fraction of aerosol that is supermicron, that is dust, that absorb the light. And then you can get a proxy of dust, and this is an example of 1 year measurements at our background stations of PM dust that has been derived by 2 different methods. this online method that gives you every 1 minute dust concentrations, and the one that is a reference one, which is a filter-based methods. So over 2 years here, very good and robust result showing that the linearity of this type of technology is about 2 orders of magnitude. So another example of a technology that is used, that can be used to monitor and provide real-time information on dust. There is more scientific instruments that can be also used for that. They are even less spread within the community. Is, for instance, this one that basically collect aerosol, put them in water, and then analyze the calcium content, which is a major component of dust. And this is the type of information we can get. This for a couple of months in Cyprus, in PM10, showing that the calcium, which is a tracer of dust, is matching well with the previous instrument I showed you before that measure the absorption of dust. So here in these things, we have very high time resolution for the two instruments, 1 to 10 minutes. So you see a lot of dynamic that can be observed with big events that are, for instance, shown in the middle. Now, what we can get because of real-time information, and that's very important because you may not get it from the first take. This graph below shows the dust concentration during weekdays and weekends, black and gray, and together with black carbon, BC, which is emitted by traffic during weekdays and weekends. And you see that every morning, there is a traffic peak except weekends, and every morning there is a dust peak. And this dust peak is dust that is responded in the air from the traffic. To give you more time to absorb my message. So the time the presentation is going back to life, I wanted to show in this graph that having high time resolution measurements of dust is critical for getting information of the dynamic of dust. You could see, we're almost there, we are here. We could see a morning traffic peak that is due to resuspension of dust from the roads, and then you see that the weekends, when there is no traffic, there is no dust in the air, very little. And you see the afternoon, this peak in the afternoon that happens very often in the region that is the development of the boundary layer, that you have breeze, you have wind that's happening over the day. And you have seen this morning that wind is a major driver of dust. If there is enough wind, you put in the air a lot of dust. So there is a kind of diurnal profile where you see also dust that increasing in the air over the afternoon just because of local wind conditions. And again, if you have filter sampling over 24 hours, like I've shown you the typical methods before, you will not be able to assess what is this type of dust from the roads, from the winds, or from the transport. Now, an instrument that has been shown in Qatar that is also running in Cyprus. So you have now on the east and the west side of the Arabic Peninsula measurements with this type of instrument, is an XRF instrument that provides a capacity to measure 70 compounds out of 67 metals. And that is great because many of sources of aerosols can be traced by specific elements. Biomass, heavy fuel, coal combustion, tie wire, car exhaust, brake wear, and mineral dust, which can be traced by aluminum, silicate, calcium, titanium, iron. So this type of instrument is very interesting because, of course, it gives you information in real time about all these sources, but also about dust. So this is an instrument that we have been running in PM 2.5. Of course, in PM10, you have much more dust. But in PM 2.5, this is a year of observations at our urban background station with this instrument. You see that if you make the difference between 1 and 2.5 micrometer, that gives you, again, the same instrument as in Qatar. It gives you that basically already everything above 1 micrometer is almost dust, and you see a perfect correlation between our dust product from the instruments and every particle that is between 1 and 2.5 micrometer. Just a confirmation of what you see in Qatar. Now, maybe more interesting, and maybe what was discussing before about aging of dust. So dust is mostly non-processed, but a small fraction can be processed by pollution. And if you look at these two instruments, you see two correlations. The first correlation in blue is ammonium sulfate, is from, let's say, in the region combustion of fossil fuel, production of SO2, condensation to form ammonium sulfate. But you see a second slope that is sulfate on dust. It's correlated with the first one because if you have a lot of SO2 in the air, you will form both ammonium sulfate and you will condense SO2 on dust. So these instruments, the two together, can give you information about aging of dust, which has been mentioned before, has an important implications for aerosol cloud interactions, lifetime of dust, cloud seeding, and rain enhancement. Now my little toys are drones, and we are operating one of the largest drone facilities in Europe, in Cyprus, and we are using it to measure aerosols. It has a big advantage and can be used on many occasions. We have been flying our drones for the validation of the European Space Agency Aeolus satellites for dust products, so it was back in 2022. And this is the type of information you can retrieve without any assumption on PM concentrations because you are doing actual measurements and not retrieval of measurements. I want to insist on this fact because remote sensing technologies rely on algorithms that retrieve PM from different assumptions. But in this case, there is no assumption. We are directly measuring PM from the drone, and this drone, as you can see, can fly up to 5 kilometers altitude over a period of an endurance of 2 hours. And you see very easily from one day to another, different layers. This is in Cape Verde, so in the outflow of Saharan Desert, that you have sometimes dust layers up to 4 kilometers, and we have been able to fly above it. Sometimes you have dust layers very close to the ground. You see, for instance, the 24th of June when we had 2 dust layers, and this, you can see them very well. The big advantage of drones as well is that remote sensing technology like LiDARs, they are not seeing any dust in the first hundreds of meters of the atmosphere where the people are living. So these types of drone can fill the gap. So these are pictures of our teams flying drones in Cape Verde. What you can get also from drones is not just the concentrations, but also the size distribution and the chemical composition. And this is an example of what you can get when you put different sensors. You have size distribution, which is very important for what? For the validation of remote sensing technologies like LiDARs or satellites, and chemical composition, which is also very important for the retrieval. And with this, you can retrieve PM concentrations from LiDARs, and this is an example of measurements we have been doing. On the left side, concentrations in situ with a drone, on the right side with a LiDAR. So you see there is a good correspondence, and then good algorithm can help to retrieve PM from that. Now, what are the different tools that can be offered to better apportion dust? So I've shown you all the technologies, and I will switch now to the methods that we can use. We can compute all this data and get better information. The first one is positive metric factorization. What does it mean? It's a kind of mechanism so that you, from the chemical analysis, you perform a kind of statistical analysis, and then you get different sources of your aerosol. So from the composition of your aerosol, you get sources, and the fraction of each of the source. And what is interesting is that you have chemical fingerprint for each of them. And for instance, for dust, you see that there is a lot of trace elements that can really trace properly the origin of dust. In yellow is a contribution of mineral dust for each of these species. Another tool that is used and has been also mentioned this morning for Qatar is the Lenshow approach. This method is very interesting because when you are measuring dust in a city, you want to know if the dust is produced within the city, for instance, by traffic, or is imported from outside the city to the city, which is transported from the region, let's say. So if you have this approach and you are measuring dust in two different locations, inside the city and outside the city, then you can apply these methods. This is what we have been doing, for instance, in PM2.5 in Cyprus. So you have a regional background in Cyprus, which is mostly sulfate-rich source, which is, you will find the same in the region here. Huh? It's not a big scoop. But you can also infer the local contribution of your PM. And in this case, if you look, this is Nicosia traffic site, urban background, and Limassol. These are the two biggest cities in Cyprus. And what shows here is, okay, domestic heating from biomass, which is the wood combustion, is very important. The second most important source is, as expected in the city, traffic, which is in black. But you see the yellow stuff here, that is dust. And this dust is exactly what I showed you before. It's the dust from resuspension due to traffic. So just make a short calculation. If you switch all cars from fossil fuel to electricity, electric cars, you will just cut by half the emission of traffic because of these dusty roads. And these dusty roads, we have shown that over the year, over the month of the year, they become more and more dusty as a function of dust episodes that brings and feed dust over the cities. Another tool that is also very useful is called potential source contribution function, is to geolocate from back trajectory analysis and real-time measurements using this type of information, where are the hotspots of whatever you measure in aerosols. And if you have real-time measurements, you can get very high precision of where you are influenced from. So these are, for instance, the source of fine PM dust we have that affects Cyprus. Just from one station, we have emissions on the, essentially from the Middle East. So we have Saharan dust from Libya and from Egypt, but the major source of dust that is impacting Cyprus is from the region here. So this type of tool is very useful because it's just the example of one station, but just imagine a network of of measurements. You will be able to pinpoint with a very high resolution what are your hotspots. Hotspots for pollution, okay, you can get also from satellites, but hotspots also for dust. And hotspots for dust are important because your model needs to know where are your sources of dust in the region. And we have seen presentations this morning that have shown already over Kuwait and upwind regions how important it is to locate these dust regions. Another tool is back trajectory, but using FlexPart. What is interesting here is that using this over a long time period, you can get classification as a function of origin. I show you here the example of measurements over a period of 10 years over Cyprus of different elements, here potassium, for different source regions. Some of them does not show any trends, some of them show increasing trends. Like the Middle East region shows an increase of potassium, which is what? Which is increasing of biomass burning. So we are influenced in Cyprus by biomass burning from Syria, from Lebanon, and climate change, as you know, is enhancing forest fires, and forest fires in this region contribute to increase the signal of potassium here. So if you don't make this type of statistical analysis, you will never be able to say that this region in the Middle East shows increase of potassium because of climate change and increased forest fires. You are challenging me here with cutting my presentation, and I have to continue without any slide support. So I will move now to the models and try to explain you that, of course, without observation and everything I've shown you here in terms of observations, the models cannot be constrained. And these models can be global models, can be regional models. They have been shown already this morning, and I think there is a special session later on where modeling will be presenting, and I think there is also some colleagues here maybe presenting some of this activity there. What is important for models is, of course, observations, but also the capacity to, let's say, run not just the observation, so you need high time resolution. What I showed you before is essential for models to be constrained. The model they can deliver you measurements every 1 hour, so they can be constrained very efficiently if you have real-time measurements of dust. If you have 24 hours measurements of dust, it will become more tricky. So models need to be fed by data, and this type of data, still hopefully no presentation coming in. I'm getting short. And so this model needs observations. And I showed you before maybe one of my take-home message, and you will be happy to stop hearing me here at this stage, is that there is a lot of initiatives that have been taken around the last few years to start to build monitoring networks. There is monitoring networks developing in Qatar, in Cyprus. We are in Cyprus trying to coordinate efforts with colleagues from Egypt, from Jordan, from Lebanon, to build a comprehensive network with remote sensing and in-situ observation of dust. What is interesting for you here is that there is long-range transport of dust coming from Sahara that arrives here. So it's important that you have a network that is upwind of your place in Saudi Arabia so that you can better predict when you have dust events coming from Africa. And this is what we are trying to build in the Eastern Mediterranean with this network. The same stand, of course, with everything you are, that is doing in the Gulf region. So we are contributing also to build such network in Saudi Arabia with the National Center for Meteorology and with Dr. Ala. So my laboratory will be supporting for chemical analysis the apportionment of PM dust for a period of a year in PM 2.5 and in PM 10. I guess Dr. Ala will present in more details with some slides the capacity of this network. But I think it's a great opportunity to start to think all together how to mutualize data, because dust is transboundary. Of course, it's local origin as well. I showed you that cities can produce dust as well. But without this coordinating effort over the Gulf, over the Eastern Mediterranean, all the effort that is done in Saudi Arabia will be not so much impactful without integrating all these observations. So I will stop my presentation here. I thank you very much for your attention. It has been a quite challenging end for my presentation. I will share hopefully with all of you a PDF of it so that you have a chance to look the end of the story, but I would like to thank for your attention and just keep this message in your mind. We are building here an early warning system, but this will work with a regional effort. Thank you for your attention. So I don't know if we should continue to run presentations without slides because it's quite challenging. So maybe we can make a few minutes break and the time to fix the technical problem, because I'm afraid that we cannot run a session with just with, like I just did with my hands and my microphone. So I give you a couple of minutes. Or maybe there is I can take questions at least. This, I don't need slides. There is someone here, I don't know if there is, maybe you can use your, there is some microphones on the tables and maybe you can try to use if this is working. It was working this morning.
Okay, thank you. I'm Mohamed Al-Saghir, Regional Directorate from Kingdom of Morocco. I have one question about models. Are there some studies can compare performance models, for example, to know this model is perfect or perform more performance in this parameter in this area? Thank you.
Thank you. Well, as you could see this morning from the presentation of our Swedish colleague, when you want to make a kind of robust prediction of what will be the climate, you take an ensemble of models. There is not one model that is doing better than the other, that is the ultimate weapon. I think we need to have an approach here that integrates all models that are currently available in the region. There are models from Qatar which are super efficient and have been constrained over Qatar. There are models that we have been developing in Cyprus, models that have been developing in Saudi Arabia. I think the magic recipe here is like the SDS portal that is in Barcelona that gives you an ensemble of forecasting products, is to use this ensemble of models so that you make your own opinion about what will happen. I think this is the best approach so far, not try to make a kind of unified effort, but try to work as an ensemble, like IPCC projections is an ensemble of models.
Hello, can you hear me?
Yes.
I'm Dr. Abdul Khalik Ansari from Pakistan. I think you gave a very good presentation and a lot of data. You showed us a lot of information and a lot of statistical data. You know very well that, these dust produced and storms and dust are natural and man-made. And all these depends upon the wind speed and wind direction. I'm just wondering, I couldn't see any information on health impacts. You talked about composition and particle size. You know very well that particles less than PM10 micrometer are dangerous, and we easily can inhale these particulates and have very serious impacts on our health. The second information which I wanted to see was about visibility. When there is a storms and there is a dust, then we always face visibility and transport problem. How we can avoid that? What measures you suggest to cope with these issues? Sometimes there is a water, moisture, and these aerosols, can be very dangerous, and they can produce haze. So, these are the serious impacts related with climate change. So I hope you will, address these issues and suggest some measures. Thank you very much.
Thank you very much. Yeah, you are touching here the impacts of dust on health, which is, as you said, function of the size of concentrations. You are touching here the impact of dust on visibility, which is also very important for many activities, transport, air traffic, etc. And I would say without observations, you cannot address them and mitigate their impacts. Health impact will be done. Here we are back to life. I will finish what I was telling. Observations are needed for health impact studies because you will work statistical data for cohorts and you need a lot of information on concentrations from a lot of places. And again, without measurements, you cannot assess the visibility. And visibility, as you said, that can be hazy. And in some places, you think that it's just dust, and it's not. I give you the example of a study we have been performing recently in Egypt, in Cairo, where half of the visibility is due to waste burning and humidity of the Nile River. If there would be no Nile River in Cairo, there would be you will have better visibility and we will have half pollution. And this is only possible because of measurements and observations. So I will really speed up my presentation because I have went much over. I wanted to inform here that, as I said, models are currently used here in Cyprus in operational mode for the forecasting. I know it's the same in Qatar. We are doing here dust air pollution links, energy forecasting and application. Example of publications we have been doing with this operational tool of WRF-Chem that we would like to implement in the region. We have heard this morning about impact of climate change and effect of dust transport of it. We are also addressing this issue at the Cyprus Institute. We are the coordinating body for the MENA Codex. Codex is the initiative of the UN for climate projections, and the Cyprus Institute is leading all the regional efforts in the Middle East, North Africa for climate change simulations, and we are using this type of activities here to address impact of climate change on dust concentrations. I was showing that our drones validate dust products of a satellite that is called Aeolus from the European Space Agency. But also this Aeolus satellite is producing winds, and having good winds can improve models retrieval, in particular of aerosol optical depth. This is a paper that we have been publishing just down, showing that with this type of new products of winds from Aeolus satellite, we can derive a better simulation of dust. Earth system models are very important, and it was mentioned this morning. So we are running also these Earth system models that can run at global scales. And examples of publications we have been doing, and some of them presented by this morning colleagues, Abdelkader. Going to new opportunities. So as mentioned before, we are collaborating with the National Center of Meteorology, and thanks for your trust, Dr. Hala. So there will be a couple of monitoring stations that will start very soon. We will be performing chemical analysis. I showed you that this is the most robust and reference technology for assessing PM dust in situ. And these labs are accredited by a number of international networks that provide quality control assurance of the data. So we will be working also with WMO from the Global Atmospheric Watch, which provides also some support for quality standards of chemical analysis. We have been collaborating in the region with United Arab Emirates and the Environmental Agency of Abu Dhabi. They have a shipping research vessel capacity, and we have been measuring in the Gulf and around the Arabic Peninsula pollution. We are continuing to do it, and we are also collaborating with the Ministry of Environment in Egypt to improve air quality observation over the Great Cairo. And we are developing what I showed you before, a tentative network for improving observations of dust in the region, which is, by the way, I realized it just now, that it's exactly the same strategy that the National Center of Meteorology is using with in situ and remote sensing. You need both, and here to develop a network that would be basically upstream or upwind of Saudi Arabia, with all these colleagues and colleagues from Jordan, Tarek, Hussein, who presented, for instance, this morning. Conclusion, take-home message. I want to remind you that there is an urgent need for real-time dust observations of dust in the region, that new technologies are now available to address this challenge. It was not the case even a few years ago. So there is a window of opportunity right now to jump in and fill these gaps of observations. A lot of efforts remains to build such network to become operational. Don't believe it will become operational one day. There is new tools that are currently under development within the region, not to rediscover the wheel, to be used as an ensemble to enhance prediction and better assess impacts. And highlighting the needs for regional collaboration, the need also, as mentioned by Dr. Rami Al-Farah, of super sites that are not air quality monitoring stations, but are really stations that you have comprehensive measurement of dust properties with a lot of scientific instruments that will improve your scientific knowledge. Currently, your knowledge on dust, our knowledge on dust, relies on studies that have been done in North America, for instance, and the dust are not the same. And there is a lack of knowledge of the typical regional dust, and there is a need for research on atmospheric dust in the region because it's unique. It's not even the same as saran dust. And there is this need of super site, of research centers that needs focus on this. I think Dr. Hala is initiating with his colleagues such initiative, which is great in Saudi Arabia. Thank you very much. I will finish with this picture of a drone in the Gulf, which is a drone for research. We have been measuring dust over the Gulf up to 2 kilometers altitude with this type of drone. So thank you for your attention. So I think I have exhausted my time of questions, but I will be available at coffee breaks if you want to discuss more with me. Now I would like to come back to the program and invite the next speakers. So the next speaker is Dr. Chandan Sarangi, I'm sorry for the bad pronunciation, will provide information on the characterization and impact of dust storms on North Indian subcontinent. Dr. Chandan, the floor is yours. You have the microphone, you have here to play the slides. Thank you.
Thank you. Yeah, thank you, Professor Jian. The background is very well set up by my preceders since the morning. My name is Chandan Sarangi. I am an assistant professor in Indian Institute of Technology, Madras, India. We are an academic group, and what I will talk about is my research on how dust is actually affecting the Indian climate to a more substantial portion than we actually believe in it. Okay, and most of my research have been funded by Indian government as well as DOE from US. Sorry, still figuring out why it's not changing. Okay, so there is a lag, I believe. So this image is itself quite self-explanatory. In between Middle East and India, in mostly half of the annual period, we have westerly winds which flow, and there is a lot of arid region which generates or emits dust, as has been put across. So whenever there is westerlies which are blowing, you can see movement of dust across the entire region. And in this figure, you can see Middle East to Arabian Sea, that region. And then once it enters, or the same winds and the same scenarios are there, it enters the Indian subcontinent. You see, okay. You see these dust transports actually reach up to the entire high mountain Asia region. So the entire North India is being affected, or the North Indian subcontinent is being affected by these plumes. I would like to show this paper. These results are by Banerjee et al. 2019. What they have done is they have used a regional climate simulation, and they are trying to see how these dust transport, or what is the contribution of dust aerosols over this entire Indian subcontinent region. And the central figure, you have the red dots, which are various aeronet sites that continuously are measuring the space in last 15 years. We also have to initiate a site in Saudi Arabia, and then we have everything in the northern Indian subcontinent. The simulations clearly show that and this simulation was done for a one year period. You can see during the summer season, mostly the dry season in Indian subcontinent, which is March, April, May, June, you will see a lot of dust optical depth rise in all these sites, and the flow is generally westerly, so it moves from Middle East towards the Indian subcontinent. In terms of percentage, this paper shows that regionally and seasonally it might vary, but in the rough order of 50% of the total columnar aerosol can be present because of the dust contribution from both regional, in a broader sense, within Indian subcontinent, and also from remote, which is mostly Saudi Arabia, Iran, Pakistan, that side of the country. Now, coming back, so if that is the picture, and this is 15-year climatology of aerosol optical depth over the North Indian subcontinent, and what you are seeing is mostly during the pre-monsoon period, which is March to June, we have a high load of these dust aerosols over the western North Indian region, and because of the flow, it affects the Indian main plains, which is also known as Indo-Gangetic Plain. So the flow moves from western, with the westerlies, it moves into the North Indian subcontinent, and it reaches even Bay of Bengal, the other side of the Indian subcontinent. And when we do vertical measurements, so we have this columnar observation which shows aerosol loading is very high. If you go for the vertically resolved measurements, you will see that these plumes are generally being known as elevated aerosol layers, and it's a persistent phenomena over the region during pre-monsoon period, where the elevated region lies between 1.5 kilometer till 5 kilometer. And there has been numerous studies in last 2 decades identifying this persistence of the phenomena. Now, these dust layers are radiatively very active. At the surface, they have a radiative forcing of order of 100 to 150 watt per meter square. And at the same time, the atmosphere is heated up by 50 to 70 watt per meter square. So the dot shows, the vertical profiles are corresponding to the dot, which is at center of IGP. And in last 15 or 20 years of Earth observations, this region has been well studied. And there has been papers now which are clearly doing the climatology of the radiative forcing. And these are all sites of aeronet sites over the same region. And what I want to highlight is, take Kathmandu. It's a Himalayan site. And you can see that the radiative forcing efficiency means how much is the decrease in radiation per unit increase in AOD of during this period. So these efficiencies are very high in number. The values goes as high as 200 watt per meter square per AOD at surface, and the atmospheric warming can go up to as high as 100, 120 watt per meter square per AOD. These are the efficiencies per increase in AOD, how much you are seeing. So just trying to set up that these plumes, or during this mostly the dry season, Indian subcontinent actually witness a lot of dust transport, which is radiatively very active or very strong, and it has a clear-cut impact on our climate. Some key observations or the pathways of these impacts has been studied in last 10 years. This is a famous paper in Nature Geoscience which talks about that this region, wherever there is the dust loading increases, and because of the atmospheric warming it creates, it can affect the Indian monsoon system in terms of creating a low pressure, enhancement in the low pressure region in this part, which will then induce the convergence of wind into the Indian summer region and can alter our predictions of monsoon. We also have seen that aerosols or the monsoon clouds, which are deep convective clouds, are very susceptible to the loading of aerosol over the region, and presence of these particles can actually lead to cloud invigoration of the system, which not only changes the precipitation intensity and the spatial region, but also can affect the surface cooling, which is our understanding about the climate change over entire Indian subcontinent region. So going forward, there is another very clear inclination of these dust storms or the dust plumes which reach India. They actually reach the Himalayan slopes and get deposited, a large portion of it get deposited over the Indian cryosphere, not only Indian, the high mountain Asia cryosphere. And then there is a definite positive loop which comes into play. So more of this deposition makes the surface darker, hence increases or hence decreases the surface albedo. It captures more energy, starts early melting, and as the surface is melted away, there is positive feedback of more emission back into the entire region, and the regional impact magnifies. So many, how these, so I will talk about some of my recent research on this in more detail, but we will, towards the end I will try to show that this is also a very clear indication of regional impact on the hydroclimate of northern India. Let's talk about the river basins over that region. We have very broadly Indus River Basin and the Ganges Brahmaputra River Basin. And there is a study in Science Advances in 2018 which actually calculated, used remote sensing to calculate what is the trend in snow melt over the region, over these different catchment basins. You can one very interesting fact which can be noted out here is that y-axis being the elevational, the change in altitude, and x-axis being the snow melt trends. Obviously, we have a understanding or a belief now that the snow melt trends are decreasing, but you can see a elevational gradient in the decrease, and specifically in the red and black color lines which correspond to Amu Darya and Indus basin, while the gold line is mostly Gangetic basin. So these two basins, being as close as 1000 kilometer, are showing very different trends, elevational trend in their snow melts. Now, whenever we look at this region and try to understand these dust plumes, this is a Calypso Pass from satellite, and we are witnessing the same dust plume from satellite observations now. We can clearly see elevated aerosol layers during the pre-monsoon period. If you use such passes over the region for last 15 years of observations, and then identify what is the spatial distribution of number of these elevated aerosol regions, layers, you can see a spatial pattern which totally dominates itself in the western side of the North Indian subcontinent, which is incidentally also the Indus river basin. And if you look at the distribution at the elevational level, y-axis being elevation and x-axis being number of elevated aerosol layers, these dusty layers, you will find that this matches with our initial understandings of ground-based measurements. So previous what I showed was ground-based measurement, and there is a clear-cut enhancement of these layers or presence of these layers between 2 to 5 kilometers. Now, this being the basis, a general logical exploration may be that these plumes might be affecting the snow melt trends. However, we don't have a clear, first of all, when we start looking at that perspective, we understand our models are not even simulating these dust plumes. Many of the models are actually not having the dynamic representation of dust. And it took us some time to actually develop the WRF-Chem model at a very high resolution to capture the vertical distribution in our dust versus anthropogenic representation. What I'm showing is, as you go higher up in your altitude, the dust contribution keeps on increasing, which is the general belief of these dust plumes coming at elevated aerosol layers. But these were, to inculcate these in the regional models, you have to have a very good boundary conditions coming into picture, which you are bringing in from the global models for this regional model. Another realization was that coarse resolution doesn't create this effect. I'm showing a comparison between the top one is satellite, middle one is a high resolution, which is 10 kilometer resolved model, and the third one is a coarse resolution, which is 70 kilometer resolved, which is much closer to the climate models we are seeing nowadays. And the impact or the distribution, the spatial distribution of the terrain and snow cover is not actually simulated by the coarse models. And we need to have a better resolved high resolution model specifically for such phenomena to be captured.
Doctor, you have 1 minute to conclude.
Yes. So once we can capture such phenomena, we actually do sensitivity experiments without these dust plumes and show that the parabolic shape elevated changes in snow melt is actually being contributed by dust these dust plumes coming into picture. This paper you can read for more details. However, I will just go ahead with a little more of monitoring activities we are now doing. So this is a region where we don't have much monitoring also happening of these dust plumes. So we started actually in campaign mode monitoring of the dust reaching these layers, and we actually go there. We have set up a site and do pit measurements to understand the dust properties, because you see, whenever we are having these dust plumes, we are unable, and these dust plumes are present at 2 to 4 kilometers in atmosphere. It's not very easy to have comprehensive measurements to understand the dust properties like aging and other. So instead, Himalayas are a site where you can actually measure these dust plumes, aged dust plumes, and understand the chemical properties. So, and these are the data collected, and we actually see that with altitude, first of all, the amount of dust which is reaching that region is quite high, which is also being seen by remote sensing and modeling. And further, we also do the aerosol measurements over there at 3 kilometer elevation in Himalayas. And we capture the dust plumes which are coming there. Once we do capture, then we use the chemical analysis method to understand for some, like there was a question, how do we know if it is a dust plume? We actually use the PM10 to PM2.5 ratio as well as the chemical characterization to understand that these events, which are dust storm events, have a very specific ratio. PM10 by PM2.5 ratios are always more than 2 if it is a dust storm over there. At the same time, if you have the black carbon mass being measured simultaneously, you will see that some dust plumes doesn't see an enhancement in black carbon. However, in some cases when the dust plumes reach there is significant enhancement in black carbon. Based on such understanding and observation, we realize that...
Doctor, if you can please conclude.
This is the last slide, sir. Okay. The dust storms that we are talking about from the modeling and the remote sensing perspective, they actually can be of two types. As we were discussing, the mineral dust dominated, which is more close to the elevated aerosol layers that has been found from remote sensing. At the same time, there will be polluted dust events which are also dominated by black carbon. So last figure I am showing, there are actually two types of dust plumes. One in which the PM10 to PM2.5 ratios, just that increases, but the BC concentration doesn't change. But in another set of dust plumes we are seeing, the PM10 to PM2.5 ratios as well as the BC concentration in the plumes increases. So there can be a clear segregation out of these two. With this, I will just summarize. The monitoring is very much needed, and the fundamental part of the aerosol plumes, the aging and the mixing state, is still not very well known. Whenever we try to model it at high accuracy to understand the impacts, we generally realize that models fail short for high radiative effect, means the dust plumes which have high radiative effects, they are not getting simulated. It's simulated at a coarser resolution. So to properly have the monitoring of the dust plume aging, which affects the optical properties and the radiative properties, bringing them into the model so that the feedbacks are well simulated. These radiative properties will definitely feedback the wind circulation around it. Getting these things simulated, we still need a lot of in situ measurements as well as going across the modeling activity and global collaboration in all sort. And we understand the dust region is not small, it's actually covering the entire globe in the center. So measurements and modeling as well as collaborated measurement sites at the other side of the continent is very important for it. Thank you. I will stop and take any questions if you want.
Thank you very much for your presentation. I propose that the questions, we put them in the end. So I would like to invite the next talker, which is Dr. Ishaq Suleiman, who will present us his work on elucidating PM2.5 pollution during the Middle East springtime severe dust events, spatial temporal trends, meteorological influences, and transport pathways. Dr. Ishak, you have 10, maximum 15 minutes. I will remind you 1 minute before the end. Thank you.
Thank you. Good afternoon, ladies and gentlemen. So I wish to stand on the existing protocols. So I'm Isaac Dimeji Sulaiman, a Nigerian working at Sand and Dust Storm Warning Regional Center at National Center for Meteorology, Jeddah, KSA. I'll be taking us through elucidating PM 2.5 pollution during the Middle East springtime dust events. Several studies and even the previous speakers have spoken about the dust events. But previous studies like Francis et al. 2022 and Mabrod 2024 have highlighted and analyzed severe dust events during springtime, May 2022, over the Middle East region. But till date, no study has really elucidated or investigated the PM 2.5 pollution during these severe dust events. These are the slides, background and introduction. In 2022, several countries in the Middle East were ranked by the WHO among the nations with severe air pollution. For instance, Iraq was ranked second, followed by Bahrain, followed by Kuwait, United Emirates, Qatar, Saudi Arabia, and Iran. And as a result of rapid development, industrialization, and urbanization, the Middle East has been suffering from severe PM pollution for more than 2 decades, especially during the springtime severe dust event. As we have known, high level of PM 2.5 reduces the air quality and atmospheric visibility, and also has adverse impacts on human health. PM 2.5 pollution is majorly formed as a result of emissions from anthropogenic activities, also natural activities, natural sources, and unfavorable meteorological factors. Regarding human health, several epidemiological studies have revealed and associated that high PM 2.5 causes several diseases and even premature death. Annually, the GDB has estimated about 4.2 million premature deaths associated with ambient PM 2.5 pollution. During this study period, in May 2022, the PM 2.5 concentration daily was as high as 804 microgram per meter cube in Dubai. So to design effective emission control strategies, so there is need to assess the spatial-temporal trends, the meteorological influences, as well as the transport pathways during the event, and also quantify the contributions of emission sources to this severe PM 2.5 pollution. Actually, the data used in this study were PM 2.5 daily 1 hour observation from the US Embassy in 7 cities across the Middle East, and they are Abu Dhabi, Dubai, Baghdad, Doha, Jeddah, Kuwait City, and Manama in Bahrain. Also, meteorological factors data were downloaded from NCDC, and the daily PM variable concentrations were quality assured. The monthly, daily, and day trends of temperature were investigated. And during this period, during the May 2022, 4 atmospheric pollution episodes were discovered, and the APE was defined as a continuous elevated PM 2.5 for at least 3 days, consecutive 3 days during the period, And in this study, the interim target 4 of WHO, which is 25 microgram per meter cube, was used to grade the APE. The meteorological influences were assessed using the ventilation coefficient. Ventilation coefficient is defined as the product of wind speed and planetary boundary layer height. Backward trajectory analysis were carried out, spatial temporal trends. During the study period, this figure shows the monthly average PM2.5 concentration across the 7 cities, and as it can be seen, so the monthly average in concentration in Abu Dhabi, Baghdad, Doha, and Dubai was as high as 65.2 to 207.4 microgram per meter cube, and the monthly average concentration in other cities are shown below. As it can be seen, definitely deteriorated air quality was noted in major cities of the Middle East during the May 2022 springtime, as majority of cities had very high, even above, except Jeddah, even above the interim target 1, which is 75 microgram per meter cube. And this figure shows the spatial temporal provision of 25 in the Middle East. As earlier stated, so many high PM2.5 concentration were noted across the cities, from Abu Dhabi, Baghdad, but the severity was very high in Dubai, as high as 800 microgram per meter cube. This is for other cities. Also, we look at the diet trends, that is the hourly variation of PM2.5 during the study period, and it can be seen that both during the day and night, there were elevated PM2.5 concentrations across the cities. This shows the maximum diet trends during the periods, as high as 903 microgram per meter cube in Dubai, and also Kuwait City. And this is the PM2.5 during the APEs. As earlier stated, APEs, 4 APEs were defined in each of the cities. Yes. So let's look at the meteorological impact on PM2.5 during the study period. So as earlier stated, ventilation coefficient was used, and this shows the temporal variations of PM2.5 and ventilation coefficients. Low VC enhances accumulation. That is, when there is low ventilation coefficient, there will be poor dispersion, and PM2.5 will just be accumulating during the period. So daily elevated PM2.5 concentrations were still observed in all of the cities, despite substantive high VCs, because in some instances, there were high ventilation coefficient up to 4,000 meter square per second, yet there was still elevated PM2.5 pollution. So this shows that the event was not only impacted by meteorology, but also by emissions. So let's quickly go to the city. So the transport pathways during the study was analyzed using the backward trajectory model, and as it can be seen across the 3 cities here, Abu Dhabi, Baghdad, and Doha, there are some instances of local sources, whereas there were instances of long-range transport from North Africa and even from the Europe into the considered site. Conclusions. This study has shown that the Middle East witnessed 4 APs during May 2022 springtime, with ranging of PM2.5 from 25 to 814 microgram per meter across the cities, and unfavorable meteorological factors such as low PBLH and WS enhanced PM2.5 pollution during the APs. Effective regional emission control strategies to mitigate future PM2.5 pollution across the Middle East are urgently suggested, and impact of chemistry and meteorology in the formation of APE must be properly understood. As I earlier said, that despite that there were very high ventilation coefficient during some of those days, there was still very high PM2.5 pollution, meaning that the pollution was not only influenced by poor meteorology, but also emissions. Recommendations. These are the recommendations. Establishment of multiple monitoring stations of PM2.5 and its gaseous precursors in the Middle East are highly suggested. Long-term analysis of PM2.5 in the Middle East should be considered in order to formulate long-term effective emission control strategies for the region. And the emission control strategies should not be at national level, but at the regional level. Source apportionment of PM2.5 and visual components, as previous speakers have said, that majority of the elements or composition of PM2.5, they are more toxic. So there is need for the source apportionment study to be carried out. And as a result of this, so we'll be considering using chemical transport model, which is WFCMAC, so to look at the source contributions into PM2.5 during May 2022 springtime. Thanks for listening.
Thank you very much for keeping the time as well. As I said before, questions will be kept in the end. I would like to invite the next speaker, Dr. Rim Al-Shamari. I apologize for the bad pronunciation. Prediction of dust storm monthly frequency in Riyadh using LSTM model. Dr. Rim, you have 10-15 minutes. Thank you.
Thank you, Doctor, for the introduction. Okay, today I will present our work, which is about using long short-term memory to predict monthly frequency of dust storms in Riyadh. And I want to acknowledge my co-authors, Prof. Mohammed Oksoi and Dr. Omar Arwais from King Saud University. As an overview, as we all know, dust storm is a major environmental hazard that affects arid and semi-arid regions. And actually, these dust storms impact the air quality, the public health, and also reduce the visibility, which can cause a lot of issues to transportation. So we need to have a predicting dust storm frequency. It's essential. Not only essential because we need to have the early warning systems and to have a planning and preparedness, but also to know what are the factors that can that can lead to these dust storms. For example, can increasing the vegetation cover lead to increasing in dust storms? And what are the challenges with the dust storm prediction? So the first thing is we have the traditional approaches, which are about analyzing the satellite imagery and also analyzing the historical data. But this is time consuming and also sometimes the critical details can be missed. The second approach is having the numerical weather prediction models. And here we can simulate atmospheric conditions contributing to dust storms. However, these models also time consuming, and sometimes it's complex, and it is difficult to make it regional and local. And the third one is having the applications of machine learning. And here there are two methods of having applying machine learning. The first one is the short-term forecasting, which is usually used as a classification for the next day, as is there will be a dust storm or not. While for the long-term prediction, it is to predict the monthly forecasting. However, the related works mainly focus on using only meteorological data, which is good to provide the dust storm frequency, but
it has some limitation in finding the environmental changes and the environmental features that cause the dust storms. So here for our study area, we are doing our study in Riyadh, and Riyadh is significantly impacted by the dust storms. But also here we include the local dust sources. And actually we have different points of local dust sources. We gathered them from previous related work by Prof. Badr al-Harbi. And these dust sources are local in Saudi Arabia. We have 15 points and we grouped them to 7 dust sources group. And here in the first plot, you can see this is the frequency of dust storm in Riyadh for over 16 years. And the color represent the different seasons. And as you can see, there are a pattern. There are a pattern of our dust storm seasonally. So we can't apply the deep learning models if we don't have a pattern. But as we can see, there are a pattern of the dust storm frequency. The data collection, as I said, it's over 16 years. The first one is the meteorological data, which include the temperature, the humidity, and also the pressure, and the other features. And the second one is having the satellite data. And here we have it to assess the NDVI and also the land use changes. And the third component is the data for the dust sources, which include the meteorological and also the normalized vegetation index, the NDVI. And for pre-processing, of course, the first step is to have cleaning the data from missing and erroneous. And the second one is feature engineering. And here we add more information to capture the temporal feature. For example, having the season number, and also the previous month dust storm frequency. And also we include the windy days in each month. The windy days for the city itself and also for the dust sources. And then we did the normalization. As we have data from different scales, we did the normalization to have them all in the same scale. After that, we did the feature selection to make sure all the features are significant to our model. And finally, we split our data to training and testing. And this is a summary of the selected features, the data sets for the data sets and also the spatial temporal resolutions and the coverage. As I said before, for 16 years, the data sources are different. It includes the meteorological data, the land cover, and the NDVI. For the methodology, as we said, we are using long short-term memory, which is a deep learning model. And it is an enhanced type of a recurrent neural network, which can capture the long-term dependencies. And here we are using it because the dust storm frequency, we consider it as a time series, and we want to capture the temporal and the seasonality dependencies. And this is our experiment settings, including the window size, which is related to having the 5 past months to predict the upcoming month. And here for the results, the first figure shows our prediction and compared with the actual dust storm frequency for Riyadh. And you can see in the figure the temporal dependencies captured correctly by the long short-term memory. And the second figure shows the residual value, which is the difference between the actual and the predicted days. And the range around adding 5 days to discarding 5 days. And for the performance and the accuracy, we try to have the accuracy for our model for each season. So we compare the accuracy for each season, and you can see the winter, spring, and summer having almost the same accuracy, but it is a little lower for the autumn. And here we used Shapley additive explanations, the Shap value, which is come from the game theory, to know the feature contribution to each of the model output. And here what we are trying to see is the feature contribution to our, the feature contribution including the environmental variables and also the dust sources features. And we can see, for example, the urban area affect the dust storm frequency, and also we have, and also for the dust sources, there are different wind directions that impact the dust storm occurrence. But from this figure, that leads us to the second one, which is to have the analysis based on the season. So we can say, for example, some of the dust sources affect Riyadh dust storms in certain seasons. And we can see, based on our analysis, for example, the wind direction from dust source number 4 affect in season 1, which is the spring, and the autumn season. And for the discussion and conclusion, as we determined the accurately frequency of dust storm monthly predictions by using long-short term model, and also the ability of the model to capture seasonality and temporal dependencies, and the importance of having seasonal analysis to the Shap value and also to our results and our model accuracy. Okay, that's it. Thank you.
Thank you very much for your presentation. I would like to invite on the podium the last speaker of the session, Dr. Ahmad Saman from King Abdulaziz University, who will present his work on temporal evolution on aerosol optical depth over the Arabian Peninsula, Aeronet MODIS Meratu observations from the 21st century.
Thank you, Dr. Sinclair. Bismillah wa salatu wa salam ala Rasulillah. First of all, I would like to thank the Sand and Dust Storm Center for the invitation to participate in this conference. And then I would just like to point out what Dr. Sinclair concluded his speech with, that we need to conduct more studies in the region itself. And another point was a very interesting idea just came to mind in connection between Dr. Reem and also Dr. Sinclair talks, is that we have an extended region of sand in the Arabian Peninsula. So is it possible to deploy a lot of instruments around all cities in the Arabian Peninsula? As we saw from Dr. Reem's presentation, we have just around Riyadh city, how many sources? 10s, 20, 30 locations that actually can generate sand storms just to affect Riyadh, right? So here, what if we can use remote sensing technologies in order to be able to better forecast sand and dust storms in the Arabian Peninsula? So here in my presentation, I would like to just show a little bit comparison between different products, which are Aeronet, MODIS, and Meratu. Before I get into that, I would like to remind everyone about the sources of aerosols. We have natural sources, such as dust, sea salt, biogenic aerosols, volcanic ashes, and we have anthropogenic sources. just like industries and agriculture, construction, demolition, infrastructure, etc. Impacts. There was a very impressive speech this morning about speeches in the first session about the impacts when it comes to health of humans. Environmental and health impacts, social impacts, economic impacts. So sand and dust storms can cause a lot of impacts to our lives. How can, or what are the factors that help generating or lifting sands and dust in the atmosphere? We need to have ingredients or favorable conditions. First of all, wind speed. It's very important. And also erodible dry surface area. Our region is one of the lowest regions to receive rainfall. And also heat. Heat can actually triggers turbulence and increase instability in the atmosphere. So there is always a mechanism that can contribute to lifting dust. Distance of travel. Of course, large or coarser particles will travel shorter because they're kind of heavier, and fine particles will travel a long distance, can reach sometimes to hundreds and hundreds of kilometers. As we saw, it can reach even to India from the Arabian Peninsula. A threshold for wind speed that can generate sandstorms or lift the sand into the atmosphere. Fine to medium particles requires about 4 to 6 meters per second, when just like slightly breeze of wind. While well-developed desert pavement, we need a wind speed of up to 18 meters per second to generate dust storm. Okay, dust sources in the region. As we see, the Arabian Peninsula, the dust spanned mostly all of it. We have local sources, Rub al-Khali and al-Dahna and al-Nufud deserts. And we have also remote sources. Sometimes we have dust transported all the way from Saharan Africa. Okay, now monitoring and forecasting aerosols. There are so many different technologies nowadays that actually dealing with aerosols and monitoring and measuring aerosols. Here I will just give a brief and simple idea about these technologies. Most of you are familiar with. I will just try to make it as simple as possible for those who don't. Observation, AOD, which is a ground-based observation, and it is commonly used nowadays in the realm as a direct observation of AODs. We have Aeronet is an example of that. Also satellites, MODIS, Meteosat, MISR, and then we have new products from NASA, which is MIRA-2, reanalysis data set, and then the modeling, atmospheric dust models such as CAM and the SDS-WAS. For this study, the question that we wanted to answer is, how good are these data? Like, for example, Dr. Reem's presentation, she relied on collecting data samples from the region. But the question is, how good are these data that she used in her study? So in this work, we wanted to investigate how good are these satellite data and reanalysis in comparison to Aeronet, which is the observation. And then we use these data sets to present a comprehensive analysis of AOD in the region. And of course, investigate the temporal trends and spatial variability of aerosols in an attempt to contribute to the understanding of aerosol dynamics. We used Aeronet, MODIS, satellite data, and MIRA-2. Aeronet, I guess, it's a global network of ground-based photometers that measure atmospheric aerosols. And mainly they are used to monitor aerosols and also validate and calibrate satellite measurements and trying to improve the accuracy of climate models. MERA2 is a reanalysis data set provided by the GMAO team at NASA. They provide long-term consistent data for studying the Earth's climate system. They started from 1980 up to date without any missing data in between or gaps. The spatial resolution is 50 by 50 kilometers. And they incorporate satellite data with AeroNet and provided MERA2 in grid points format. As for MODIS, MODIS is the key sensor at two main satellites, Terra and Aqua. Terra is the morning time satellite orbiting Earth from north to south, and Aqua is the afternoon crossing for our region, satellites orbiting Earth from south to north. For this period, we depend or rely on AeroNet. Starting from 2000 to 2023, we selected 4 stations. KAUST at the west coast of Saudi. The data are available from 2012 to 2022. Solar Village in Riyadh here from 2000 to 2013. It discontinued then, and then now I think it's operatable again. Kuwait University from 2000 to 2010, and then there's like a 9 years gap, and then again from 2019 to 2021, and Masdar Institute in the UAE from 2012 to 2021. Results of this basic statistics, the correlation, we see MERA, Aqua, and Terra for KAUST, Solar Village, Kuwait University, and Masdar Institute. We see there's a very good correlation between all data set with AeroNet. Index of agreements, also very high. Mean bias error, we notice very small numbers, and they are all in negatives, meaning that all these data sets are underestimating the AOD, and the root mean square error, they also are very small. So it is promising. Scatter plot showing the 3 different data sets. We see that for KAUST, most of the observations are compact around the average line, meaning that they are highly correlated. Solar Village, we see the same pattern. And Kuwait University is also showing the same pattern. And lastly, Masdar Institute, it's also showing the same patterns. Now, we see the figure to the left. We have the seasonal averages of AOD for KAUST. We see the AeroNet in blue color, and the rest, MERA is the orange, Aqua is the gray, Terra is the yellow. And all the data sets are underestimating the AOD in comparison to AeroNet. Mostly, the most aerosol concentration actually are taking place in the spring and summer. If we look at the right side, we have the annual plot for AODs, and we see the top line, the blue one is AeroNet, and the rest of the data sets are also following the exact pattern, showing very good agreement with AeroNet, except that they are all underestimating the values. The same scenario is true for Solar Village, and also Kuwait University and Masdar Institute. This also, at the end here, this is a scatter plot using the AOD of AeroNet and the angstrom exponent using an algorithm to define or characterize the aerosols types. So whatever values are under the 0.5 value here, meaning that these are dust, and what for the points between 0.5 and 1.5, this is mixed type, meaning that we have dust particles, and we also have anthropogenic particles. And for the values greater than 1.5, this is almost biomass. So for all of our forestations, mostly or most of the aerosols are dust particles or mixed between dust and anthropogenic aerosols. So to conclude here, all data sets are highly correlated with AeroNet. The problem with AeroNet and also MODIS is that there are gaps in the data set, so we don't have a continuous observation. The only continuous data set is MIRA-2. And then for all stations in the Arabian Peninsula, most of the aerosols are dust particles. Recommendation, we need to deploy more AeroNet stations in the region, and we also need to improve MIRA-2 data with further research. And in addition to that, satellites can be really promising. We just saw that there's a very good agreement between satellite data sets and AeroNet. So the question that comes to mind now is, all of these previous talks have addressed a lot of technologies, modeling, in order to help providing a solution for the dust storms issue. The question is, okay, if we increase the vegetation within within urban areas, we might help mitigate the impact or the local impact on human. But as we saw from the Arabian Peninsula map, most of the sand and dust storms come from rural areas. Is it logistic or is it possible to deploy a lot of instrumentation in the desert? Or can we just rely on satellites and try to conduct even more research, trying to improve it to reach the level where we can actually help in early warning, which I think is the only thing that's in our hand. And thank you.
Thank you very much for your presentation. Now we have a couple of minutes for questions to the panel, so I would like to invite you. If you have questions, raise your hand. Here, if you can please use the microphone. Go ahead, if it's working.
Thank you. Yes, it's working. Thank you very much, and thank you for the very interesting presentations. My name is Letizia Rossano. I'm the director of a center that is called the Asia Pacific Center for the Development of Disaster Information Management. We participated in the workshop that was organized back-to-back with this conference yesterday and day before here in Riyadh on sand and dust storms. And I just wanted to bring to the attention of this conference a work that APTIM has produced, which is a risk assessment in Asia and the Pacific of the impact of the socioeconomic impact of sand and dust storms. And we looked at some of the sectors that we've been discussing today, including the impact on glaciers or on the production of solar energy that I see it's on the agenda later today. So I really invite you to take a look at this study, as well as the subsequent intergovernmental agreement that we've reached in Asia Pacific. So many of the countries, or some of the countries that I've discussed today are involved on how to tackle a regional plan of action on how to tackle the impact of sand and dust storm in the Asia Pacific. So I'd be very happy to provide additional information on this in the margins or during the break. And thank you very much again.
Thank you for your announcement. Do you have questions for the panel, or it was just the announcement? No question. Rami, you have a question.
Thank you, John. Dr. Ahmed, I noticed in one of the plots at the very end, you refer to biomass burning sources. Can you comment on that in this region? Where do you expect biomass burning to be coming from?
I think because of these data were collected in the urban areas, so it is close to, the data sets are collected within an urban areas, so I think that's because of the urban activities around the measuring station.
Thank you. Other questions? Yes, please.
My question is to you, how to join the network that you demonstrate within your presentation for error quality monitoring. And the second question is for Ishak. Have you studied the role of atmospheric river in transporting the dust to the Middle East area? Thank you.
So I will start first. Well, I just propose scientific collaboration network, starting by exchanging knowledge, building capacity within each country, and I think this conference is the great place to start discussing about how to enhance collaboration. So I think that's the way I see it, how to work together. This is the network I'm in. Thank you.
Thank you.
Sorry, role of what?
The role of atmospheric river in transporting dust.
Atmospheric?
Atmospheric river.
Rivers.
It is a river combined from high concentrations of water vapor. It comes from long distance, and sometimes it can transmit some aerosols like sea salt or other pollutants.
Okay.
So
no.
I mean, have you focused on
No.
the role of atmospheric river in transporting the dust in your episode of 2022?
No, not yet. But
Thank you.
it might be considered in future studies. Probably if we use a chemical transport model, because we can get unlike trajectory backward analysis, it could only give probable transport pathways. But we can use chemical transport model to know the concentration of PM 2.5. We can use the source regions.
Yeah.
So we have what we call source regions in chemical transport model, CMAC, that we can know the quantity of PM 2.5 that is coming from certain region into the specific site.
Thank you.
Thank you again for your participation. I think we will close the session at this stage. I would like to thank again all speakers. I think we have to close. I mean, questions can go and run after the session, so please feel free to contact the speakers. So I would like to thank again all speakers for your presentation, and I would like to stop here the session of today and give you the floor for the...
Thank you, Dr. Jean Siag, for chairing this session. I would like to invite His Excellency Dr. Jamhan Al-Qahtani, the Executive Director of WMO, to honor the speakers. Start with Dr. Jean Siag, the Chairman of the session. Dr. Shandan Sarji. Dr. Ishaq Suleiman. Dr. Reem Al-Shammeri. And last but not least, Dr. Ahmed Samman. Ladies and gentlemen, with this session we come to the conclusion of the first day. I'd just like to draw your attention tomorrow. We shall start at between 9 and 9:30 a.m. With the opening ceremony under the patronage of His Excellency Engineer Abdurrahman bin Abdul Muhsin Al-Fadli, the Minister of Environment, Water and Agriculture. He will be inaugurating the opening ceremony. نود أن نلفت عنايتكم إلى أن غدا سيكون إن شاء الله بإذن الله حفل الافتتاح تحت رعاية معالي وزير البيئة والمياه والزراعة المهندس عبد الرحمن بن عبد المحسن الفضلي بين الساعة 9 إلى 9:30. ندعوكم غدا لحفل الافتتاح، والآن ندعوكم إلى تناول طعام الغداء في المكان المخصص له في القاعة هذه في المطعم. We'd like to invite you for the lunch, or let's say early dinner for some of you. It's in the next hall. Thank you very much, and see you tomorrow. Wassalamu alaikum wa rahmatullahi wa barakatuh.